to our nice, wonderful live of the AP Calculus FRQs for AB and BC of 2026. Now we pause the music and we go to the main camera. Hello, how's it going? I believe the music is gonna be gone for the rest of the live. I apologize for the fellas that are viewing from home right now. But yes, so I saw some quite interesting stuff right on the FRQ things, right? They were posted a little early, so I apologize if the live is a little like an hour early, right? I realized while I was like studying physics a few minutes ago, but essentially, yes, we started early, and that's fine, right? That's completely fine. I already got my FRQs on me right here, okay? And just as a crucial thing, piece of information, the questions that are different between the AB and BC exams are number 2, number 5, and number 6, right? So this is how the thing is going to work out. I'm going to go to my next. Thank you, Taurus. Thank you, Taurus, for telling me I was muted. Oh man, sorry about that. Sorry about that. Quick, brief explanation of whatever I just said in the previous 2-3 minutes I was muted. So, the unique questions, okay, that are different in the A, B, and BC exams are number 2, number 5, and number 6. So we're gonna go for all the AB questions first, and then we're gonna tackle the last different 3 BC questions. Okay. So just keeping that in mind, we're working with Zoom Workplace right on here. No, I like that. I like this board a lot. Okay, just zooming. There we go, zooming out perfectly. And I'm gonna go in chronological order, right? So we're gonna go questions 1 and 2 and so on and so forth, right? I have decimals right here, also ready to go. So when I need decimals, I will bring that tab right around here. Right, let me just make this slightly smaller. It's kind of covering all the screen right now. Make this smaller. There we go. Right, so when we actually need decimals, I'm going to kind of bring it up here in this tab, right, and then we're going to use it, okay? Let me see if I can hide this bar. Yeah, hide sidebar. I don't need the sidebar from Opera GX right now. So, let's start. Let's start with our wonderful questions. I took a peek at a couple of them, and I actually kind of really like the fact that the format for these questions is slightly different from the 2025 one that I took. So this is going to be interesting. So here, section 2, they call it. Well, section 2, part A, of course, graphic calculator is required for this part of the exam, etc., etc., etc. Okay, so let's take a look at these. Question number 1. Oh, okay, this is a mailbird's question. Okay, I have my pen ready to go. I believe we have a nice color. Yes, perfect, beautiful color. So, and they also make it a little darker so we can see much better. So, number 1, male birds of a certain species arrive at nesting area over a 30-day period. Okay, 30 days, I like this. We already have this in our little nice table, right? This is a tabular question. The rate at which the male birds arrive at the nesting area at time t days is modeled by a differentiable function. Okay, so it's differentiable, therefore it's also continuous, all right? That may be useful in something like a justification later on, okay? I'm just looking at the chat right now. In this one, can get 35 the third question and miss one FRQ. What score can I expect? Let me think. I'm not quite sure of how the international version looks like. Is this us questions? The questions I solved were different. So I went to the AP Calculus, the AP Calculus FRQ questions from the previous years, okay, on CollegeBoard, and I'm solving the ones that are showing up right here. Okay, those exam questions. There may be different. I am not quite sure. Okay, of how different they can be. Sometimes they're just in a slightly different order, but that's essentially how the thing is going to go, right? I'm just going to go from the ones that are posted on the CollegeBoard side, okay? All right. I got a 40-minute study for 3 days. You got this, Wrath. You got this. I believe in you. Going back to the question. Sorry about the little distractions. Differentiable function, m of t, where m is the sheer number of births per day. Okay, so actually, because we have births per day, we can actually think of this as a rate. Right, m of t is technically a rate function. So selective values of m of t are shown at the table. We have all these pretty nice values, right, of the births that arrived. So now they tell us approximate f prime of 7.5 with average rate of change over this interval. Show the work that leads to your answer, indicate units of measure. Pretty good. So this right here is essentially just asking for the derivative at 7.5 days, right? It's actually pretty simple because these sort of approximations, okay, they are required, they were required for us to use average rate of change, right, or AVOC, so people call it. Okay, and that's just as simple as taking the average rate of change with this table, right, with m of t, okay, highlighting that part, from 5 to 10, right? So we just use our classic slope formula. So right now I'm just going to write m of 10, okay, minus m of 5 over 10 minus 5. Okay, that's essentially how we're going to approximate. Okay, this is just going to be the approximation of the derivative of m at 7.5. Okay, so this is how we're going to do it, right? So we have m of 10, right? As we look in our table, when t equals 10, m of t equals 16. So now we have 16 minus m of 5, right? m of 5 right around here, right? When t equals 5, m of t equals 7. Okay, so 16 minus 7 over, okay, 10 minus 5. 10 minus 5 is just 5, okay? Leading to our final average rate. Oh, wait, that's true. I said AROC. Oh, I'm sorry. My apologies. AROC, right? AROC. I don't know why I had the V thing. I don't know. I kind of just forgot. My apologies. But yes, average rate of change. My apologies again. So, going back to this thing, right? We have 16 minus 7. This is going to be a total of 9. If I'm not wrong, my math doesn't fail me. 9 over 5. Okay, and that's essentially already the approximation here, right? That's already one part of the point. But let's also highlight. They mentioned we need units of measure, right? So we have to be kind of careful here, okay? We already know that m of t here is a rate, okay? That's a rate. We already know it's in births per day. Now, usually, okay, when we deal with these sort of stuff, right, and we take the derivative of something, right? Well, usually we just set the y over the x, or in this case, our m of t over the t, right? And right now, what we're essentially doing with that, okay, let me actually keep that in the board. Essentially saying we're gonna have births per day over day. Usually that would just look like births per day squared, right? So the proper units of measure for this thing will be 9 over 5, or approximately 1.8, okay? Births per day squared. There we go. That's essentially how we'll perform this nice move. Right now, over 5, 1.8 births per day squared. I don't think the chat has any questions so far, so we're gonna keep moving. For part B, okay, this is a good one. So for part B, will births per t squared also be fine? Let me see. So t squared. Here's the thing, though. We require specific units of measure, right? Because we require specific units of measure, right? The time that they gave us here is days. So I believe the way to get like all full credit for that question will be, well, that part of the question will be days squared, right? I'm not quite sure. Maybe partial credit gets you t squared. They may get partial credit. That will be later on when they reveal that little nice sheet with all the grading system. Could say births per day. That's also another way of saying it. But usually we also go for the approach of births per day squared, right? Like acceleration, right? You have m of s, right? Yeah, sorry, m over s, meters over second, but you also have acceleration, meters over second squared, right? Anyways, going back to part B here, we have a midpoint Riemann sum with 3 subintervals: 0 to 10, 10 to 20, and 20 to 30. So this is actually going to be pretty simple. We actually just have to kind of go straight forward with 3 different rectangles, right? So that is for us to approximate, right, integral from 0 to 30. And we have to show the work that leads to our answer. Perfect. So we have to go in those nice looking intervals. We go from 0 to 10, 10 to 20, and 20 to 30. Right, and this is the midpoint Riemann sum. Therefore, let's say that these are our intervals. I'm going to actually do it with this different color, where we have from 0 to 10, from 10 to 20, and from 20 to 30. Okay, and we have to grab that middle value, right? And luckily, right, for the question here, because of the table, we have the middle value, which is right in between 0 and 5, and 0 and 10, which is 5. Between 10 and 20, we have 15. And between 20 and 30, we have 25, right? So those are the outputs that we're going to use for our nice rectangles, okay? Now, also to highlight, for our nice Riemann sum, we also need a delta x, right? That's going to be a little width of our rectangle. So what will that be? Well, that will be essentially just be the overall integral, right, from b, right, well, from a to b, so it'll be b minus a, to get a little difference, over the amount of subintervals. In this case, we have a total of 3 subintervals, so this is going to be b minus a over n, where n here in this case is going to be equal to 3. So we have a total of, well, b here, that's going to be our 30. A is going to be our 0. So we have 30 minus 0, which is just 30, over 3. Right, so we have 30 over 3, which now equals 10, right? That's our delta x. So let's work with that. We're going to go rectangle by rectangle, right? To go a little easy, right, on this thing. Not jump too straightforward. So, for the first rectangle, 0 to 10, right, we'll have to take a look at the output of m of 5. Okay, so m of 5 times delta x. Right, that'll be the width of the first rectangle. So m of 5 in this case is equal to 7. Actually, let me do this in a slightly more space around here. Oh, not what I wanted to do. We need slightly more space around here. So let me take these good fellas and move it down, right? And let me also kind of like label every time that we finish a question, right? We put a little nice tag or a different color. I think I would like that, yes. So this is part A, okay? That's part A, then we follow for part B. Okay, for part B, so this is our first rectangle, m of 5 times delta x, plus, and then we have the other rectangle, which will be m of 15, okay? M of 15 times delta x. Last but not least, as you may have inferred, the logic goes for m of 25 times delta x, all right? So m of 25 times delta x. Now you may notice that all these guys share a greatest common factor, which is in this case the delta x. So we can also simplify this by saying delta x, right? And then in parentheses we have m of 5 plus m of 15 plus m of 25, right? Now just to make this thing a little more straightforward, we already know the delta x is equal to 10, right? We know 10, then we have m of 5, right? We'll always have to, you know, show the work that leads to our answer, even though we have to use calculators, right? Even though the calculators are required. Even though these are sort of simple calculations, it's still good to, you know, write that full work, right? So we have 10 times m of 5, okay? M of 5 in this case was 7, plus m of 15. M of 15 over here was 6, okay? And m of 25 around here was 2. Okay, that was 2. Pretty good. So let me actually kind of highlight them, right? To just kind of like understand, okay, here we're going to use this output, here, 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 right? The red square represents essentially our output, right? Our height of rectangles. Height of rectangles, there we go. So now we just have to compute this. Okay, and how do we compute this? Well, we could go for the approach of the calculator, which isn't bad at all. It's completely valid, right? Where is my calculator? There we go. So here we could just write something that looks like, oh, need a little more space. There we go. We have 10 times 7 plus 6 plus 2. In this case, we have a total of 150. A pretty number, actually, to kind of finish with. So we have 150, right? Now, part B has 2 little sections for the answer, right? It has I, right, which is already finding the approximation. This is what we have done successfully, right? We have 150, so the integral from 0 to 30 of m of t dt is approximately, we're using this symbol, I like that symbol a lot, 150. But then the next part of the question asks, interpret the meaning of this integral from 0 days to 30 days of m of t dt in the context of the problem. So let's just go back quickly, right? We remember, right, that this is just a problem about male birds of a specific species arriving at an area, right? So we're getting a little more birds over and over and over. But here's the thing. M of t is not exactly the amount of birds, right, for each day. M of t is a rate, right? It's the amount of birds per day that we get, right? So it's essentially just a rate. For us to actually figure out, right, the amount of birds, we usually will have to do the classic of, you know, integrating a rate, right? When you integrate a rate, in terms of t, usually, right, with these context problems, you usually just get an amount. And in this case, we're getting rid of this day thing, right? Because as you may have noticed, we're integrating, let me go back here. We're integrating m of t, which is birds per day, with dt, right? And dt here just represents an infinitesimal, I think that's how you say it, amount of time. So we're just going to call this thing also day. And by simplifying this, right, birds over day times day will just leave you with the amount of birds. Okay? So essentially how this thing kind of looks like right now. My phone just sounded, I don't know why. Okay, so this essentially will be the amount of birds. That's essentially what the integral here is giving us. The amount of birds that we have, okay? But let's go step by step, okay? So the integral does give the amount of birds. But what do the actual integral bounds represent, okay? Well, they're telling us, okay, that from t equals 0, right, from t equals 0, the day equals 0, all the way to t equals 30, so to day 30, okay? What's going on here, what's going on here is that there's a total of 150 birds that arrive all the way from t equals 0 to t equals 30. Right? That's essentially what the problem here is telling you by itself. Now, here's a little thing. They don't actually give us an initial amount of birds, right? They don't give us an initial amount of birds. And let me also take a look at, for some reason, I feel like the live is having a little bit of trouble. Oh, no, the live is fine. My apologies, ladies and gentlemen. As I was saying, they don't give us an initial amount of birds, okay? They don't give us an initial amount of birds, which is completely fine, okay? Because of that, we can actually just infer, okay, so this is the total amount of birds that arrive from t equals 30, well, sorry, from t equals 0 to t equals 30. So the actual way of framing the question, well, this is a little I, then I, right? We'll be saying the integral from 0 to 30 of m of t dt, I don't know why I'm doing it in red, but it's alright, I like the color red, says that from the day 0, right, day 0 to the day 30, okay, a total of 150 birds arrived at the nest. Okay, total of 150 birds arrived at the nest. That's essentially what the integral here is telling us. This is how you will break down the problem in context, well, break down the question in context of the problem, okay? And I believe that should get you maximum points for all part B, right? Those solving the midpoint Riemann sum properly, and then the context of what's actually going on here, okay? So pretty good. We're having some nice progress around here. All right, let's take a look. Okay, this is interesting because previously we were dealing with male birds. Now part C introduces a couple more functions, right, regarding female birds, okay? Regarding female birds. So here, basically what they're telling us, let me just make sure that my, yes, my microphone is working properly. Excellent. Peak. Absolute cinema. So, part C here is telling us the rate at which female birds, okay, of the same species arrive at the same nesting area, and maybe taking that into account, okay, now that I just realized we're talking about specifically male and female birds, right, in different sections. So maybe here I want to be a little more specific, okay? Maybe here, when I'm mentioning, sort of birds here, maybe I want to specifically mention male birds, okay? Highlighting this is very specific. We have to be very specific when we're, talking about these sort of questions, okay? So, those were male birds for part B. For part C, we have a new piecewise function, which I kind of like, okay? F of t, again, is also birds per day, so we know that f of t is a right function, okay? And the function defined as follows. So, f of t equals 0 from t equals 0 to t equals 15, okay, interesting. Well, right before 15, right? The defined value t equals 15 actually is represented here because of the less or equal to. Okay, this is just a less. So, got to take that into account. Okay, so they give us some nice piecewise functions. They give us a sine function, which is also pretty cool. And they ask how many female birds of this species arrive at the nesting area from t equals 15 to t equals 45. Right, so the setup for your calculation run to your answer to the nearest integer. So basically what's going on here is we're working with the exact same problem as part B, but backwards, right? In part B, we have to solve for the integral first and then analyze what's going on. Here they tell us what already is going on, right? There's the amount of female birds arriving at the nest from the day 15 to day 45. Okay? So this is day 15 to day 45. And they ask us how many female birds arrived at the nesting area by that time. Okay? So now we have to show the setup for these calculations, which is not too crazy because we already did it previously, right? We're essentially representing the integral, right? The integral, because remember, this f of t here is birds per day, so it's a rate. From, not 0, actually. 0 was a previous one. Now we're going from 15, right? Day 15, t equals 15, to t equals 45, okay? Of r of t dt. Okay, and what actually is being, represented here? And it's pretty interesting. Well, we know that according to the piecewise function, right, our nice f of t behaves this way, right, going from 15 to 45, okay? It behaves this way, like this function, 18 plus 16 sine of pi over 20 times t plus 15, okay, in the close parentheses over and over, 2 times. So, with that, okay, you can also write the answer for this question, okay, and let me actually kind of highlight this here. Right, we have part C here. Sorry for not highlighting it before. I always forget. So from 50 to 45 of just that function, right? 18 plus 16 sine of pi over 20, right? Of t plus 15. There we go. Why are we doing r of t instead of f of t? So the r of t, I'm guessing you mentioned the r of t here because of the right thing that I mentioned previously. So right now I'm just using, RT. Oh, sorry. I just realized. Oh, my apologies. My deepest apologies. No. It's not R of T. No, it's an F of T, right? That's the notation for the female birds per day function. Thank you very much, Offbet, for that, for that observation. My apologies again. There we go. That's the proper function, right? I just got a little confused because usually when talking about rate functions, I always like to use r of t. But yes, you're right. We're supposed to use f of t here for proper calculations and nice work. So, going back to this thing, we just integrate all of that function, right? From that time to that time, from 15 to 45, right? And the quickest way to do that, of course, is what our nice looking calculator. Where's our calculator? It's right here. So let me actually make this a slightly smaller because I don't like the way that it's covering a certain part of the screen. That's better. Perfect. So, now my calculator is going to go integral, right? Int, usually I just write int, from 15 to 45, okay, of our nice looking function. So we have 18 plus 16, okay, sine of pi over 20, right? That's already one part of the parentheses, and the other part here, something inside of the parentheses here, we have t plus 15, right? I believe in the pre-calculus exam, you will have to kind of break down what this thing is, talking about, period, amplitude, but not required here. We go straight forward, do our integral from 15 to 45, and we get this nice number. We have 641.85 and something. Now, here's the thing. The question is specifically required for us to answer, right, round our answer to the nearest integer, okay? Nearest integer. Therefore, I'm going to grab this pretty number around here. But here's a little trick, okay? Here's a little thing that may or may not, be a nice consequence. Maybe you can get a point off or not. I kind of forgot about the rules there. But here's a interesting part here. You may see that we have a nice long decimal, so maybe not so nice, of 641 point something. However, you're not able to round here to 642, even though you have an 8 here, right? Because if you have something above than 5, you round, to the next number. But here's the thing. You can't do that here because you can't exactly just show up like 0.2 something out of a bird, right? And saying, okay, so the total here is 642. So usually here, when rounding for this, sort of context, the specific amount of integer, right? Integer amount of birds that we have here is actually technically 641. Okay? technically it's 641. Therefore, okay, even though the decimal goes 641.859 something something something, you technically have to round it to the nearest bird, in a way of saying it, the nearest integer, which will be 641, right? Because you can't just make second bird appear when you don't actually have the full amount for the second bird. That's silly. Yes, I also believe that it's a little silly, but that's essentially how the logic here of the math works. So technically here we have a total of 641 female birds that arrived into the nest. Okay? So that's something we'll have already so far. That's all part C. It's essentially kind of straightforward. And then for part D, let's take a look. On the interval 15 to 30, right? So times between 15 and 30, the difference in the rates at which males and female birds on this species arrive in the nesting area can be modeled by the differentiable function d of t equals m of t minus f of t. Makes sense, you know, that's a little difference function, right? Still a rate, okay, because we're doing operation here, where we're subtracting one rate by the other. Then why will say they Then why will they say round? Well, that's the thing. You have to be able to reason through the problem and round it carefully. Okay, I know it seems a little straightforward, right? Maybe they give you points for the 642, right? But from my past experiences with the AP exam, right, and some practice that I did in the past, in these sort of context for the problem, right, you have to make sure you actually analyze, break down little by little logically, right, the actual total amount of integers that you have, right? In this case, you can't make, like, let's say we have the 641 answer right here, right? Let's say I will make this a constant a. So this is constant a. And I get a and subtract 641. Okay? That will technically leave me with 0.85 birds. But that's not a full bird, so I cannot round it to 1, even though the math will say yes. Okay, so we're going to be careful with those. Now, going back to part D. Okay, going back to part D here. We have d of t equals m of t minus f of t. Okay, that's the classic difference. You know, d of t here is a rate function, where f is the function defined in part C. Is there a time in the interval 15 to 20 where d of t equals 0? Okay, that's actually something that I like plenty of. So, they give us an interval, they give us a function, okay? And something to highlight here is that from 15 to 30, okay? From 15 to 30, this function right here, f of t, follows this pretty sine curve, right? And that pretty sine curve, okay, technically doesn't have a single discontinuity, right? It's essentially a regular sine curve. We don't have no asymptotes, no holes, no weird stuff. Okay, even though it's a piecewise function, here we're talking from the interval 15 to 30, right, which is in between this little 15 to 45, right? 15 to 30 falls in between those values, right? Keeping this in mind, okay, what we're going to do is we're going to little by little apply, and I believe if I'm wrong, please tell me. 100%. I'm not I'm not a machine. I'm not able to like get perfectly scored questions, but I'm doing my best, you know, get to the accurate ones, okay? So here we're actually going to use the IVT, okay? Also known as intermediate value theorem, okay? The intermediate value theorem is essentially just telling you, hey, if you have just some interval a, t, b, right? From so some, in this case, some time t between a and b, okay? And you have something like f of a, okay? Is between, actually no, essentially that's what the IVT thing is saying, right? The IVT tells if you have a function that's continuous, okay? Highlight that part, continuous, okay? Must have continuity. Then, okay, let me actually also write that, and continuous. Then there's going to be some output, right, from this value t in between f of a and f of b, right? The output between f of a and f of b. So yes, so it'll be something like this. Then get this. Essentially, that's essentially how the thing works nicely. I was trying using it, but I thought it won't work because you don't know there will be an exact time where those functions have the exact same value. Interesting. Wait, sorry, I got a little confused. So using that won't work because you don't know there will be an exact time where those exact same value. Well, here's the thing. Okay, here's the thing. Technically for this IVT problem, you don't have to go too straightforward towards m of t or f of t. Okay, you have to focus on d of t, right? You must know if in d of t, right, d of t is 0 in between these values. So we know that d of t is, we know that d of t is continuous, right? Because we're grabbing a continuous function. In this case, we're grabbing from 15 to 30, my good friend right here, f of t, okay? The rate of the female birds. And they also mentioned previously that m of t, the rate of the male birds, okay, that is a differentiable function. Therefore, it's also continuous, okay? You see, everything in the problem is always connected, right? It's something very, very pretty that I like about the exam. But it can also be kind of tricky, so I can't blame you for that. Okay, going back to this nice, pretty thing, okay? Going back to this nice, pretty thing. Basically, what we have to do now is think, okay, so first, what's d of 15? Okay, we have to get our outputs first to actually figure out, okay, is this in between, right, somewhere? So first, d of 15 will be known as m of 15 minus f of 15, okay? So for m of 15, the thing's actually going to go pretty straightforward. We can just look back to our table. You know that m of 15 here is a total of 6, right? So it'll be value 6 right here. 6. And then f of 15, okay? F of 15 is going to be a little more complex, but not too hard, okay? Because we can actually go back to the calculator and use this. I will carefully take out the parts of the integral here, right? We're done with the integration for this specific part. Let's just stick to this thing, okay? I'm actually going to write it as f of t equals this. There we go. Now we have a nice sine curve, kind of hard to see, but there it is. Pretty sine curve. And now we can solve for f of 15, right? In this case, we get the output of 2, okay? So this will be 6 minus 2. In this case, we have 4, okay? If I know how to add, that will be 4, okay? So d of 15 equals 4. That's pretty nice, pretty straightforward. D of 15 equals 4. And then we have to look at the other little number, right? The other time t, which in this case is 20. So we're looking for now d of 20. Okay? D of 20, in this case we have m of 20. Sorry. M of 20 minus f of 20. Okay, pretty good. D of 20 equals m of 20 minus f of 20. Okay, in this specific instance, right, in this specific instance, we again do the exact same thing, go back to the table. Okay, when t equals 20, m of t equals 5. Okay, so m of 20 here will be 5 minus f of 20. So again, going back to the calculator, and this is instead of 15, now we have 20. Now we have a long decimal. Okay, not bad, not bad. We have 6.686 something something something. Okay, 6.86 something something something. Okay, so we gotta be careful here. We gotta be kind of careful because, you know, rounding and doing that crazy stuff can be a little odd, but it's alright. We can always kind of like round to a decent decimal. Here they don't exactly tell us where to round. Okay, so I will recommend, my best recommendation will be to you to do the actual calculation a little more straightforward in decimal. So for example, here we do 5 minus f of 20, okay, which is going to give you the exact same number. And it gives you something that goes around, okay, something that goes around like, there we go, negative 1.6, okay, 86, and stuff of sorts. Okay, so essentially, this is essentially d of 20. This is d of 20. Okay? Now you can see here, okay, you can see here there's actually a nice looking, not exactly a pattern, right? But I already have the pieces for the, you know, for actually answering the question. So, okay, the question itself was, is there a time t in this interval where d of t is going to be equal to 0? Okay? If we know, okay, if we know that our nice output here is going to be in between, well, technically d of 20 is a negative number, so that's the one we'll put first. Negative 1.686. Okay, is between d of t, okay, d of t, which is less than, okay, and then we have d of 15, which in this case was 4, okay? According to the mean, not mean value theorem, it's my fault, IVT, intermediate value theorem, okay? According to this, there is indeed going to be some time t between 15 and 20 that gives me an output that's between negative 1.606 and 4. And luckily, okay, 0 is indeed between these guys, these two values, right? So negative 1.6086 is between 0, which is in between 4. Okay? So the slightly more formal way of stating, this answer will be saying, yes, due, okay, and this is how I'm going to word it, due to the IVT, right, or intermediate value theorem. You want to write all the word, even though I will recommend just kind of go for the abbreviation, right? So you kind of just save a little bit of time in the writing. Due to the IVT applying to D of t, okay, and here's something you have to highlight 100%. Since D of t is continuous, well, continuous, no, I kind of forgot how to say it, sorry. It's continuous between the intervals, right? 15 is less than t, which is less than 20, okay? Since D of t is indeed continuous between 15 and 20, right, because we actually also figured that out, through f of t being continuous in that interval, and m of t being differentiable, therefore continuous also at that interval. Okay? And I'm not quite sure, okay, I'm not 10,000% sure if here you will have to mention because m of t and f of t are also continuous. All right. For example, I will have written that just to make sure, right? This is completely optional, but important. Okay, because this is actually how we know that D of t is continuous at that interval. Right? It's important. So highlighting that specific part here. Okay. And also, well, okay. I'm also a little silly. I just realized that there's one part of the question that I didn't read. Okay? Going back to this. Okay? The actual question straight up tells you differentiable function D of t. Yes. So this actually will save you a little bit of time in terms of, instead of writing the M of t, F of t thing. Okay? Because D of t is continuous. Okay? Because, D of t, if differentiable, okay, also continuous. There we go. So because we know that D of t is continuous, right, because it was differentiable, therefore it's also continuous, okay, the IVT, applies, yes, to the IVT applying to D of t, since D of t is continuous between 15 and 20, and, okay, D of 15 and D of 20, okay, being, I will just write it this way. Likely there's a slightly faster ways to simplify the answer. Negative 1.606 and 4. D of t will be equal to 0 since, okay, negative 1.606, well, 686, sorry, is less than 0, which is less than 4. Okay? So this, okay, is the way that I will write it in the exam, okay? Is the way I will write it in the exam. Let me also highlight, this is part D here. This is the way I will highlight it on the exam to get full marks in part D. Okay? Yes? Are we clear with that? Chat, I think the chat is completely agreeing with me. Maybe, I'm not quite sure. Perchance, yes. No. Maybe. We never know. Anyways, going back to this nice pretty thing. So now that we have all this question, okay, I'm gonna see if I can either take a screenshot, okay, see if I can just either take a nice looking screenshot for this. So the little thing just looks a little dark. There we go. So that goes into my nice folders. There we go. But in any case, I believe I can also export this, right? So export this in PDF. Okay, I like the PDF format. Okay, I like that. Oof, it's give me a minute. Okay, yeah, I think that's fine. That's perfect. There we go. It has been exported as PDF. All right. So I'm going to be saving these PDFs. Also, sorry if I didn't mention it because of context. I'm also going to be saving these PDFs later and putting them in a Google Drive so you can take a look at all the notes and the solving the problems that we did anytime you want. Okay? But with that aside, let me take all of this and goodbye. Thank you very much for paying attention for this first question in A, B, and BC. Now we're going to tackle this next question. Now for this, let me quickly go to my OBS and switch this to specifically AB question number 2. Okay? This is AB question number 2. Highlighting that part. Ooh, and I like this one. This is going to be about areas. Actually, I don't know if I like that a lot, but it seems quite interesting. That is indeed true. So let's take a look at this. Function f is defined by f of x equals 1.43 to the x plus 0.57, and the function g is defined by g of x equals 14x plus 12 over x plus 12. Okay, not bad. The graph of f and g intersect at the points 1 and 2, and a and b, shown as figure 1. Okay, ooh, sorry, not bad at all. Now, I do believe that because these graphs are so huge, we're actually going to have to kind of split this thing into 2 nice parts, right? To actually look at the question and then look at the, well, functions, okay? So I'm going to just do this for the love of the game, okay? For x is greater than 0, the equation g of x can be rewritten as this, right? So I believe this function right here, h of y, is essentially just g of x, but in terms of y, okay? Essentially just in terms of y. So do not fear too much, okay? Where h is a function of y, the graph of x equals this, and the horizontal line. Okay, so where h is a function of y, the graph x equals h of y, and the horizontal line y equals 3.5, which is that horizontal line you can see right here. Let me actually highlight it with this horizontal line. Okay, this is y equals 3.5, are shown in figure 2. So let's go step by step. Okay, this is going to take a little while, but it's going to be a pretty interesting question in my opinion. So part A, let R be the region bounded by the graph of G. Okay, so first, graph of G, the x-axis and the y-axis. Well, the y-axis and the vertical line x equals 1. We have plenty of stuff in here. We find the area of region R. Okay, not bad. So you can see here, okay, you can actually see here this little portion R here. Now, you got to be careful, okay, because there's specific curves. Okay, there's specific curves that actually don't correspond to this little section R. For example, here, this y of x, you see that little nice curve that follows this path, okay? This curve right here, that will also be this. So you're going to be very careful with the actual bounds you tend to analyze, okay? Our g of x is specifically this portion, okay? So basically what this is, this thing's telling you, this is the y-axis, this is the x-axis, this is x equal to 1, and this is g of x. Find that area R, okay? And that's actually pretty straightforward, okay? This thing's actually extremely straightforward because this area R, okay, as always, the integral represents area under the curve. So our nice answer for part A would just be the integral. Oh, no, let's keep it in blue. Integral, okay, from x equals 0, which is essentially represented by the y-axis, right, x equals 0, all the way to x equals 1 of g of x, okay, g of x dx. Okay, do not forget that dx part. That's happened to me in the past. Just speaking out of experience, okay? So with that in mind, okay, likely, you know, because we're still in part 2, we're still allowed to use our calculators. So again, I recommend you guys to go in here. I'm going to take this progress out from the part A question and go for writing g of x, right? G of x equals, let's recall it. It's 14x plus 12. Okay, let me actually put this in parentheses. I know how decimals work here. 14x plus 12 over x plus 12. Okay, that is essentially our nice looking function. Here it looks slightly different because, you know, domains and the graphs that they have to show, etc. But it's all right. This is our function g of x. The way to find our answer for part A is just the integral from 0 to 1 of g of x dx, which is a nice looking thing right here. Nice looking number. So find the area of region R, so for your calculation. So the setup is actually pretty straightforward because we're essentially just getting this integral and solving it, right? So according to our calculator, the thing kind of looks like 1.51. I believe it had some 3's in there. 51333. Now I believe you can also just kind of round this thing. Maybe just want to go to a straight answer, let's say something like 1.51, also completely valid. Okay? So that's essentially the way to find answer on part A. Pretty straightforward. For part B, region R described in part A is the base of a solid. I know how this thing's going to go. We're talking about cross sections. Yes, we're talking about cross sections. This is what I'd like to see. So, the base of a solid. Our region R is the base of a solid. For this solid, each cross section perpendicular to the x-axis. Okay, and what does this thing mean? Well, perpendicular to the x-axis would just be the y-axis. So all of our nice cross sections are going to look like this, right? There's technically kind of just like an above perspective or an above point of view of our cross sections. Okay, but because they're perpendicular to the x-axis, okay, so they're just essentially aligned to the y-axis, then we're just going to be using regular outputs. Is this what you all AB peasants were struggling with? Maybe. We never know, okay? We're not judging here because of anything that people struggle or didn't struggle with. It's completely fine to me. So you guys did your best. I believe in you, okay? You guys got this. So, going back to the little cross-section part, okay? Region R is the base of our solid. And for this solid, each cross-section perpendicular to the x-axis is a rectangle, okay? So, oh man. Please don't start a war in my chat. I want my chat to be peaceful. Okay. The rectangle, okay, for each of our cross-sections, okay, to keep it in mind, the height is going to be 1/3, okay, or 1/3 times the length of the base. So what is it? How are you being, man? I have been wonderful. Thank you very much, Matthew David, for asking me that question. Thank you. It reminds me of the things that people always ask, right? Like, people ask, like, how is the teacher in terms of, like, how good of a teacher he is, but then they don't ask, how is the teacher feeling? But thank you for asking, Matthew David. So, going back to this thing, I'm getting a little too sidetracked. So, 1/3 times the length of the base. What does that mean? Well, we know, okay, let me actually kind of try to make a nice drawing around here, okay, because unfortunately, Manim here is going to be a little limited, right? We can't exactly use Manim of some nice live representations, but we're doing our best. Is this AB? Yes, this is AB. You can see right on top of my camera, you can see it right around here, okay? Right now, we're working in the AB FRQ, okay, number 2. Going back to this thing, let me actually make this a little more flat perspective, like that. So this is our y-axis, okay? Y-axis, x-axis, and the thing kind of looks like this, right? That's essentially, it's kind of how g of x looks, okay? Make some dotted lines here. Okay, this is x equals 1, x equals 0, okay? So for the base of our rectangle, okay, I'm going to use red. This is going to be our base. And the base here essentially is just the output, right? The output g of x. So base here is just going to be g of x. But then we also have a height. And the height here that's specifically mentioned is 1/3 times the base, right? 1/3 times the length of the base. Well, what does that mean? That means that our height here is just going to be 1/3 times g of x. There we go. Nice. And then at the very end, it says, write but do not evaluate an integral expression that gives the volume of this solid. Okay? And it's actually pretty straightforward. Remember, when you are working with cross sections, you're thinking about integrating an area function, right? Or maybe area of x, dx, or stuff of sorts. Okay? Now we have to think in terms of context. What's the area of our nice rectangle here? Okay? What's the area of our nice rectangle? For Demos Coach, who is asking for the BC thing, don't worry. We're going to go through BC when we finish with these questions first. Okay? I'm trying to go for AB first. And then we're going to tackle all of BC, because BC only has like 3 questions that are different on the FRQ. Okay? So just kind of like separate this thing, split them up a little nicely. Okay? Going back to this thing. Okay, what's the area of our rectangle here? Well, we know that, usually area is equal to base times height. But in this case, our base is g of x, and our height is 1/3 times g of x. Okay, so let me actually start putting this in my integral. So this will look something like the integral. Okay, still, remember the boundaries. Okay, our boundaries here are still going from 0 to 1 because we're talking about region R. Okay, the region R described in part A. Those are the boundaries, 0 to 1. So we're still working from 0 to 1 of our area function. As I mentioned, the area is base times the height. So our base, g of x, times the height 1 over 3 g of x dx. Okay, this is what you have to evaluate to get your full marks on this question. Okay, and how do we do that? Well, first you can kind of simplify the thing. Like, for example, this 1 over 3 is a constant, so you can send it to the front of the integral, right? So 1 over 3 integral from 0 to 1. And because you're multiplying g of x twice, you can just say g of x squared dx. Okay? And with this in mind, technically, okay, and let's actually be careful because you're not quite done, okay? Because g of x is a specific function. Leaving it as g of x, I don't think is going to give you full marks. So I will personally recommend you, if you did it, hopefully, is to write 1 over 3 integral from 0 to 1 of actual g of x squared. So it'll be 14x plus 12 over x plus 12. Going back to this thing. 14x plus 12 over x plus 12. And this squared times dx. Okay? This, you don't have to put it in your calculator because, look, they say, write but do not evaluate. Just write the expression that gives the volume of the solid. This already is supposed to give us the volume of the solid. Okay? That would be the way for us to solve this question nicely and easy. Okay? I remember on the MCQ part, I didn't know the formula for an isosceles right triangle cross section. I feel you. The isosceles right triangle is a little tough. Okay, I believe in the worksheet that I put on my video, right, on the description, I mentioned it, like the isosceles cross section. But it's actually not too hard. Okay, because according to, you know, deriving all the stuff that you have to do and all the cool integral stuff, or, you know, figuring out little by little, you know, breaking down into pieces. The isosceles triangle is just grab your top and your bottom, right? There's little pieces in between your function, right? That part of your base. Then you square that and divide that by 4, if I am correct. I may be wrong. No, it is. It is. So basically for the isosceles one, okay, for isosceles cross section, that's essentially talking about integral from a to b, right? 1 over 4, okay, you multiply by 1 over 4, and you just get your base, right? Or your, base squared dx, or your f of x, or your top minus bottom, right? Top minus bottom, if you're working that way, top minus bottom squared dx, right? That's essentially how the isosceles works. Sorry for the little sidetracking, going back. So part B, we already solved part B nicely and easy. Okay, part B was actually pretty neat, pretty simple, pretty straightforward, and I liked it. For part C, let's go. I'm trying to go slightly slower. I may be going a little too fast. Sorry, I got a little excited. Haven't done this sort of calculus in a while. Well, except for, you know, making the video. So, the shaded region in figure 1 is bounded by the graphs of f and g. Okay? So region in figure 1. So that's figure 1 right here. You see that little shaded region? That's what the thing's talking about. From x equals 0 to x equals a. And when it says x equals a, you remember this coordinate point they talked about? That's what they're talking about, right? Little coordinate point A. Okay? And then they say, find the area of that shaded region. Okay, this is where things actually get quite good. Okay? For finding the area of this specific shaded region, okay, you may notice there are actually two small pieces to this region. Okay, we have this piece right here, where f of x is greater than g of x. Okay, so f of x will be our top and g of x will be our bottom. And then we have this other region where the things flip for a minute, right? Where g of x actually is larger than f of x. So what does that mean? What does that actually mean here? Well, for us to properly solve part C, we have to break this down into two integrals. Okay? No, we also have to highlight something. They tell us to find the actual area of the shaded region. But for us to actually find that area, okay, we actually have to find what A is. Okay, we have to find A. How do we find A? Well, the good thing is they already gave us f of x, right? They give us a function f of x, 1.43 to the x plus 0.57. And if we go into our nice decimals and write that, f of x equals 1.43 to the x plus 0.57. Okay, and you zoom in a little, then you get the exact same setup as the question right here on the paper, right? So you have this first part, right, from 0 to 1, right? We already know that little section here, right? points. Well, technically, these are points 1, 2. Okay, this is point 1, 2. Oh yeah, I'm actually gonna leave it a little closer. Sorry, point 1, 2, and then you have the other point AB. So if you go here, you take a look that you have indeed your collision point 1, 2, but then the other guy right here, A, okay, is actually equal to 3.25582, etc., etc., etc. Now, technically, we do have to show calculations for that. So how will we find A? Well, for finding A, it's actually pretty simple. You just do f of x equals g of x, okay? You set f of x and g of x equal to each other and solve for x, okay? Now, okay, from my understanding, you don't have to do all of the solution and, showing you find your A properly, as long as you're able to, state your A formally. Like, for example, in this case, x, they only collide 2 times in this nice little interval. So we have x equals 1 and x equals A. In this case, A here specifically is, let me go back here. There we go. 3.25582. 3.25582. Okay, this is the A that we're working with. This is our A. Okay, that's the A that we're going to be working with. We got to be careful, okay, because rounding this A early in the problem could get us to some hard rounding problems, right? Now, gladly, this is not physics or chemistry when you have to do, significant figures. Funny enough, I was just learning about those previously, but no, that's not the case. Here, the case is we're going to have to be working just with the straight value, okay? So you can either just bring this thing as a point, and just use this whole nice looking decimal, okay? Or you could try and solve the thing manually, but that could give you some problems. So I will recommend just try to go for this accurate decimal, because that will likely just get you enough, enough decimals to get to your nice area answer. Okay, but enough japping. Let's keep going with the actual thing. So as I mentioned previously, we're breaking this into 2 integrals, because here the tops and the bottoms switch, and they actually talk about this in a video. I think it was kind of halfway on the applications of integrals. Okay, so the first integral here, okay, we're talking about terms of in terms of x. So we're going from x equals 0. That's where this part here starts. X equals 0 all the way to x equals 1. Okay, from x equals 0 to x equals 1, and then we do top minus bottom. Now here our top, as you may see carefully, is f of x. Okay, here our top here is f of x. This line right here, that's supposed to be f of x. So we're going to write here f of x, and then our bottom is g of x, right? That's the one slightly below this guy right here. So this has already giving us area between curves. That's pretty good, but we're not done yet, because there's only one part of the shaded region. The other part, okay, this is plus, is the little blue region right here. And this one goes from 1 all the way to A, or in this case, all the way to 3.25582. Okay? That's how this one here goes. So 3.25582. Oh man, sorry, I'm a little hungry. So from 1 all the way to A, okay, that's how this one looks like. But here, our g of x is the top function, and f of x is our bottom function. So we will have to write g of x minus f of x. Okay, and actually, let me not forget the dx here and here. Okay, very important parts of the integral. We got to be very careful. Okay, and this essentially will give you the actual total area. Okay, now here's the thing. In the previous one, it said write but do not evaluate. Here we do have to find the area, so we have to evaluate it. Okay. Now, if you wish, okay, if you wish to write this thing as like the full functions, okay, you could do so, okay. But just for keeping it kind of brief here, I'm gonna skip the actual writing the whole function, right? Like the 14x plus 12 over x plus 12, or the 1.43 to the x plus 0.57, because mentioning f of x and g of x already kind of go pretty straightforward, and I believe that should be enough to get full marks. Okay. If I am wrong, please correct me, but I believe that's enough. So we already have our g of x, g of x and f of x set up in our nice decimals. So we can go straight forward and actually, write the things down. So integral from 0 to 1 of f of x minus g of x, okay, dx. That already gives you some part, of the area. We're not done yet. So that's 1. Then the other is plus the integral from 1 to my nice value of a. So that is 3.25582. That should be good. And then we write g of x. Now g of x is the top. Minus f of x, the bottom. Dx. And this, okay, adding these two integrals leaves me a total of 0.63178 something, something, something. Okay, so as I mentioned, we round these things a little to make this thing quicker. So the area, the total area of the shaded region is 0.632, okay, or 6317. Well, no, 6318, sorry. 0.6318, okay, approximately. So let me actually correct this thing properly. Approximately, there we go. So it's approximately, you know, when you add both those areas between curves, you get this pretty number. Okay? So essentially how the thing looks like, pretty good, pretty straightforward. I actually like part C a lot. That was actually kind of simple. Okay? So that was part C. For part D, things seem like they're going to be kind of interesting. And I like it. And I also don't like it, because I don't know if maybe I'm going to mess up. Hopefully I'm not going to mess up. We're gonna try to do this carefully. And also, thank you, my bad for distraction. It's completely fine. Demos, do not worry about the distractions. We're here to learn. And also, you know, proceed to understanding where we also, you know, able to properly get a 5. Now, give me a very quick second, chat. I'm going to just go for a bottle of water and be right back because I am dying of thirst / hunger. Well, that was a fast break. Sorry about that. Sorry if people didn't have a time to actually, you know, catch some air. But I definitely needed to. So, oh, I feel so much better. So sorry guys, I love water. Water is like my favorite drink in like all of history, even better than Coke or orange juice, etc. Going back to this thing. Part D. Let T be the region bounded by the graph of x equals h of y. Okay, not bad. This is our region T right here. Actually like it. And the horizontal line y equals 3.5. Okay? And they say write but do not evaluate an integral expression that gives the volume of the solid generated when region T is revolved around about the y-axis. Okay, this actually was relates to one of my favorite parts of the video, which was the visual for disk and washer methods. Now, luckily here, okay, you may notice that we're revolving this around the y-axis. This axis right here. Okay, we don't have an outer and inner radius, okay, because we're doing this, you know, we're revolving this around the y-axis, right? This is our axis of rotation. So, that means that we're just going to use regular disk method just in terms of y. Nothing too crazy. Actually goes pretty straightforward. So you guys may remember that for disk method, okay, let me actually write this part D. DS for disk method. Huh, kind of cool. Disk method. Here, when you want to find a volume, you multiply pi times the integral from a to b of your function. In this case, it was going to be in terms of y, f of y dy. Okay, but your function is squared, right? Because here your function acts as a radius for plenty of circles, filled circles, or disks. Okay? So keeping that in mind, let's actually break this down. Here we're actually going to use h of y. Okay, not f of y, but h of y. So for this problem, we'll have pi equals the integral. Okay, and then we have to go not in terms of x. Okay, previously we were working with integrals in terms of x. But now, because we're working with a function in terms of y and dy, we're working with values of y. So actually I like to look at it this way. This is the value of y where we're starting, right? This is kind of like where t actually starts. Okay? This thing right here. This value of y equals 1. Going to do BC FRQ 2 after this, please. Actually, I kind of like that format. I actually do like that format. Well, I will consider it. I believe I actually like that format a little better, right? Going through the AB question first and then the BC question, you know, kind of get them a little mixed up, right? People, you know, taking their time to take a look at AB, BC content. I like your idea of that, so let's actually do that. I like that a lot. But first, let's finish D here. So, our first boundary is y equals 1, and then we have the line y equals 3.5. not bad. Right, this is the region, so this little segment here, we're going to kind of just ignore it. Okay, so this is our nice boundaries. We go from y equals 1 to y equals 3.5. Okay, and then we grab our nice dude h of y and square it. H of y squared dy. Pretty good, pretty nice. So this, okay, in theory, I believe these calculations are proper. Hopefully they are nice and easy and pretty for all of you fellas. Okay, this is how you will have to solve, nice, right, our nice question here, part D. Because, again, they also mention right, but do not evaluate the integer expression that gives the volume of this solid, right, this revolved region T around the y-axis, right? So if you want to be a little more specific, you could go for the approach of pi integral from 1 to 3.5 off, and you big parentheses because maybe you put the whole h of y thing, right? Maybe you want to write something like 12y minus 12 over 14 minus y squared, right? You have to square your function in terms of y. Now this is the option I will prefer. Okay, I like this one better. There we go. I like this little option a little better, right? Because you're being a little more specific. That's the actual kind of like whole expression besides just saying h of y. Okay? So this, I took AB and my FRQs are completely different. So here's the thing. I am following the FRQs that were posted just today, okay, on the CollegeBoard website. Okay? Here they posted the AB and BC FRQs, and I'm just following those ones. Okay? My apologies if I am covering a question that you didn't see just yet. Okay, sometimes they also like to, kind of mix them around in terms of order. Okay, they just mix them around in terms of order, but I'll believe that they should essentially be the same. If they're not the same, my apologies. I'm just going to be covering the ones that show up in the CollegeBoard website. But thank you very much, dude guy bro, for mentioning that last part. So, there we go. This is essentially our nice looking part A, B, C, and D for question number 2. Now, I do have to highlight, I am taking a little longer than usual, for these questions. These questions go a little more straightforward, but that's why I'm here. I'm breaking them down, so that's why I'm taking a little longer. So, again, we're going to, are there different versions? I thought there was only one main version. That's what I think. I think that there's only one main version, and they just kind of mix the order of the questions. So, my recommendation will be for you not to worry too much about it, okay? But, going back to this thing, I'm going to export this as a PDF. Like this a lot. So file name, I'm just gonna call this thing FRQ AB. Okay. There we go. Nice. Again, I'm just in case, because you never know what's gonna happen, I'm going to zoom in nicely and easy and take a screenshot, and then we'll proceed. Nice. Nice screenshot, I like that. So with that said, let's deselect these guys, take out everything else. Let's proceed with the next question. So now we're actually heading into part B. All right. So unfortunately, I do have to mention here the calculator is not allowed anymore. But let me not forget. Actually, I almost forgot. That did mention something that I do want to do, which is covering now the second FRQ. Okay, FRQ for BC. So let me actually put this in my OBS. FRQ BC FRQ number 2. And let's go for it. I have the PDF just right here for us. Okay, so let me actually kind of just take this guy out for just a minute. Okay, I can always bring him back, don't worry. He will be back. Right, okay. The AP Calculus FRQ will be back for Avengers Doomsday. It will be back for Avengers Doomsday. Are you international? If you mean about international student, not exactly. I did take the AP Calculus exams in America. But if you're talking about foreign student, then yes. Oh man, that water tastes delicious. All right, BC free response questions. So if you go here, flip the pages, you may notice question 1 is the exact same as AB. Question 2 gets a little more crazy. All right, this one is actually about one of my favorite topics, even though it wasn't my favorite back then when I actually had to solve it, which is in this case polar curves. So let's go for it, shall we? Let's take a look at this. So, let me actually kind of bring this guy back. and put it below. Yes, that's exactly what I'm talking about. We're just gonna hide him. This was a nightmare. It's alright, Alpha. I know you did great. Even doesn't matter. I know that you did an excellent job for this one. Okay, trust yourself. Yeah, look, the ones that were posted by CollegeBoard, they're completely different. I know what happened. I know what passed, and it's so much easier. So this guy, bro. Hopefully, I believe you did your best. I believe in you. I know that you did great in your AB/BC exam, like you did the BC exam. Okay, but don't worry. Right now, I'm just going over the questions that CollegeBoard posted. Okay. I've been party of this question. Oh no, man. It's alright. It happened to me too. Back in 2025, I also took like, I didn't even solve part C or D. They took too long for me. It took a while for me to actually, like, realize what was going on. So, I can't blame you for that. Okay? Let's take a look. Let S be the shaded region bounded by the graph of the polar curve. Good thing is that there's only one polar curve in here. Hopefully not a second one is going to show up out of nowhere. So, R of theta equals 3 plus 2 sine of 2 theta plus cosine of 2 theta. I actually like this one a lot. It does look a little bit like a peanut. I believe somebody mentioned something about, like, the graph looking like a peanut. But this one does look like a little cat cut in half. This goes from 0 to pi. Not bad. And it can be shown that R prime of theta equals 4 cosine of 2 theta minus 2 sine of 2 theta. You know, it would be funny if this thing was actually not given and you have to solve it. It won't be too hard, actually, but it'd be kind of cool. Calculator shall be in radian mode. Thank you very much, AP exam, for reminding us. Yes, this shall be in radians. Always in radians. If you have it in degrees, be very careful. Usually that will work for stuff like physics or etc. Part A. Find the area of region S. So set up for your calculations. So here, stuff goes actually pretty straightforward. Okay? We gotta be careful because, as I mentioned in the video, if you just do integral of R of theta, d theta, this is accumulated radius. This is not the area of the actual polar curve. Okay? I would actually recommend you to take a look at a Khan Academy video that actually breaks it down beautifully. But the actual area, okay, the way for us to find the actual area inside of a polar curve is doing 1 over 2 of the integral, okay, of R of theta squared d theta. This is how you get the area of your polar curve. And that's exactly what we're going to do right now. So, breaking that down, we can actually kind of just write it a little straightforward. We can write it as A equals 3, no, sorry, not 3. Whoa, that was too fast. 1 over 2 integral, okay? And also, remember, the boundaries. In this case, the boundaries are already given to us, right? This specific polar curve goes from angle 0 to angle pi. Okay, and something that I like a lot about polar curves is that we're also drawing the thing counterclockwise, just like you will usually go for regular angles. Okay? So here, your angle goes from 0, okay, angle 0 to pi, okay, of your R of theta squared. So R of theta here is going to be 3. I was so happy that they gave me the bounds. That's true. When they give you the bounds, you're gonna say, praise the Lord. It was wonderful. It was wonderful when they give you the bounds. I believe on the 2025 one, they didn't give bounds. I can't remember quite well, but every single time I see it and they don't give bounds, it hurts. Anyways, R of theta equals 3 plus 2 sine of 2 theta plus cosine of 2 theta squared. Don't forget about the last part, d theta. Okay? And when solving this, it actually goes pretty straightforward because, again, you jump into your calculator. Okay, we're still in the part 2, technically. So we're still able to use a calculator. Let me bring this thing up. Much better. So, with this, okay, we have 1 over 2. And actually, something cool I can do, I can go to decimals and change the grid. I actually like this grid a lot. Okay, 1 over 2 integral from 0 to pi of, and let's write it little by little, right? Maybe later, okay, if you want to just save a little bit of time, I'll recommend you to write R of theta as a function itself, and then just put the thing in the integral later. So R of theta, we know it's 3 plus 2 sine of 2 theta. Okay, plus cosine of 2 theta. Okay, I believe I wrote it properly. 3 plus 2 cosine of 2 theta plus, yeah, plus 2 sine of 2 theta plus cosine of 2 theta. Excellent. Nice. So with that, I can write R of theta here and square it, and then write d theta. And that, my friends, is how we get the area of region S. In this case, you can just round it to like a simpler number. They don't exactly tell you what you have to round it to, but I would just go for like 2 decimal places or 3 decimal places, but it looks a little more pretty. So we'll go 18.064, I believe I saw. I may be wrong. Let me take a look. 0.64. Yes, excellent. Not bad, not bad, not bad. All right, that was actually pretty good. Part A was pretty straightforward. Now, part B, C, and D is usually when people take a look at polar curve questions and they're like, I don't want to do this. And I feel you. I also was in that state when I did mine. Okay, let's keep going. There's a point in the curve at which the slope of the line tangent to the curve is -3/7. Let's be careful. Step by step, what is this thing saying? They essentially tell you that in all the polar curve, there's going to be a point, okay? There's a point at which the slope of the tangent, the line tangent to the curve, that's basically just saying the slope of the line tangent, that's essentially just saying dy dx, okay? This dy dx represents the slope of our tangent line, as I mentioned in my video. And we know that dy dx will be equal to -3/7, okay? So the slope of the line tangent to the curve is -3.7. Let me just highlight that. Perfect. These are not my BC FRQs. As I mentioned, I grabbed these ones from the CollegeBoard website. Some of them may be a little different. Some of them may be a little shuffled. But these are the ones that maybe most people got. I'm not quite sure. So hopefully you guys are still interested in taking a look at how the other BC questions went for. Okay? Anyways, going back to this thing. At this point, dy d theta equals 3 square root of 2/2. And they ask you to find dx d theta at this exact point. Now here's the problem. They don't exactly tell you where the point is. But here's the thing. You don't need it. You don't need to know where the point is, because you already have enough information to find dx d theta. And you'll say, well, Isaac, well, we only have some rate of change here. What do we do that? How do we do there? It's all right. Because one of the cool things about polar curves and parametric curves is that they share the nice property of the chain rule in Leibniz notation. What does the chain rule say in Leibniz notation? Well, we usually know that dy dx, okay, it usually kind of works like a little chain, right? They connect the variables together. They look like dy dt times dt dx, okay? But you'll say, wait, we don't have something like dt dx, okay? T here could be any variable that's not x or y, okay? And in this case, we're actually working with the variable theta, okay? Part of it was actually easy, making me question if I was doing it correctly. Exactly. Sometimes like these questions are actually pretty simple and straightforward, and then you're asking, did I do this right? But yeah, no, it's happened to me. Don't worry, Alphabet. It's happened to me too. Anyways, let's keep going. So technically here, we can also use d theta for the chain rule, right? But here, the actual chain rule that we're going to focus on looks like this. dy dx equals dy over d theta over dx over d theta. This is the exact same thing as this. It's just a little more rearranged, and we're not using t, but we're using theta. Okay? Same exact results. This is how you're supposed to find dx d theta. So let me actually just mark this thing as part B. This is part A, part B. There we go. With this in mind, okay, the thing goes even more straightforward. Because if you're able to rearrange this in terms of dx d theta, you got this in the bag. Okay, let me just multiply by dx d theta on both sides. Okay, dx d theta on both sides. So now dx, and also, okay, I'm going to divide by dy dx on both sides. Dy dx on both sides. How does that look? Well, at the end, dx d theta is the exact same as dy d theta over dy dx. Oh, dx. Sorry. dy dy. That won't make sense. There we go. So, pretty good, right? Now, we just have to essentially plug in the values that they already gave us, right? So, dy d theta, they mentioned at this point it was 3 square root of 2/2. 3 square root of 2/2. Okay, or over 2, however you want to write it. I'm going to write it this way. Over dy dx, and we know that the slope of the tangent line is -3/7. So it will look like -3/7, like this. Okay? You can also go even more straightforward and just plug that in your calculator. Okay? But you still have to highlight this part. Okay? As I mentioned, show the work that leads to your answer. You have to state how these things are, building up clearly, even though you may use your calculator. Okay, so dx d theta at the end equals, so I'm just going to use my calculator for this. Okay, let me just go a little more down and write 3 square root of 2 over 2. Okay, and this over negative 3 over 7. Okay, looks a little hard, so if you want to write it in maybe a different notation, you can just use the division symbol, I believe. So 3 square root of 2, that's 2, divided, oh, never mind. The symbol just writes a fraction. Then just keep it like this. Okay, you got to be careful, you know, you have your dx d theta on top, dy dx on bottom. Well, I'm sorry, dy d theta on top, dy dx on bottom, and you're all set. Okay, with that said, you can just write this nice number that you get, which in this case is negative 4.95. I'm going to round it. Okay, negative 4.95 approximately. Okay, negative 4.95. Pretty good. Nice. So that was part B. Not bad. Pretty good. Pretty straightforward. Let me change some colors a little bit. Whew, give me a minute. I need a little bit of water. Delicious water. So now we have part C. So I find the value of theta for the interval between 0 and pi over 2 at which r has a critical point. Interesting. It's actually going to be kind of cool. Sorry, ladies and gentlemen, I still need a little more water. I should have definitely brought a snack with me before doing this, but it's all right. I'm fine. You guys trust me. So, interesting. So here they mention where r has a critical point, and we usually know that critical points happen when your derivative, okay, in this case dr d theta, we're going to be working with that one, equals 0, okay, either 0 or vertical tangent line, so usually undefined. But for this one, I believe it's going to be a little more clear if we go for this 0 approach, okay? So dr d theta equals 0. But remember, your angle has to be inside 0 and pi over 2. If it goes beyond that or less than that, not counting it. Not counting it at all. So how do we do this? Well, it's actually pretty straightforward. They already gave us our prime of theta, which is 4 cosine of 2 theta minus 2 sine of 2 theta. Are these int? Spideys, if you mean integrals, the first question, part A, that was indeed integrals. Okay? Oh wait, if you mentioned international, not quite sure. Okay? Going back. R prime of theta. We have to set this guy equal to 0. So let's do it. Okay, I'll go slightly down. Okay. I'll write 4 cosine. I said I would change colors and then it went back to red. 4 cosine of 2 theta minus 2 sine of 2 theta. I don't know why they gave you the derivative of less. That's true. That's true. You could have figured out the derivative yourself. It's actually pretty straightforward. But thank God they already gave it to us directly. So we set this thing, r prime of theta, equal to 0 to find our critical points. Okay? And that later on leads us to maybe solving for 0. Well, sorry, for theta, technically. So we have stuff that looks like 4 cosine of 2 theta, which equals, okay, I'm just adding sine of 2 theta, 2 sine of 2 theta on both sides, plus 2 sine of 0 plus 2 sine of 2 theta. So it kind of looks like this now. 2 sine 2 theta. Okay? And you can also simplify it a little more. Maybe divide this by 2 on both sides to get rid of that 2 if you wish. Okay? Cosine of 2 theta. Oh, and sorry. 2 cosine of 2 theta equals sine of 2 theta. Now you may wonder, well, what's going on here? How do we find the angle? Well, here you can also try to go for a little more hard approach, which is trying to straightforward use some trigonometry. But for the sake of likely everybody that took the exam, we're going to be going back to Desmos. Okay? Going back to Desmos, the way that I would like to go for this approach is hide my polar curve just for a minute. Okay? Let me actually write this thing as pi because it's showing the full polar curve. There we go. So I'm going to hide it just for a minute. And I'm going to write 2 cosine of 2 theta. Okay? 2 cosine of 2 theta. Now, usually, if you write theta, it's not going to look very pretty. Sometimes if you write r equals 2 theta, it looks like this, like a polar curve. So what I will recommend is for you to use x instead of theta. Just for a minute. Bear with me. Okay? It makes it easier because now you can take a look at your actual nice-looking graph. Then you do the exact same thing for the sine of 2x, right? And now, okay, you have to take a look at when are these guys colliding, right? When are they intersecting? Okay, but we're specifically taking a look at where are they intersecting between the values of 0 and pi over 2. Between the values of 0 pi over 2. Okay, so what does that matter? Because if we go beyond that, we could get a different value. The answer, unfortunately, is not valid anymore. So we got to be very, very careful. So we already know that pi over 2 is right around here. So if you wish, sometimes I like to do this, is just writing x equals 0 and x equals pi over 2 to know in between what part of the graphs I actually have to look into, which in this case is this. And as you may notice, the purple curve and the black curve, right, these two cosine of 2x and sine of 2x, only collide at this point right here. This value is 0.55357. Okay? Yes? Now, something that I do find quite interesting is I am not quite sure if you're able to round this value. Okay? I'm not 100% sure if you're able to round this value and plug that as your answer. Because technically, this is indeed between pi over 2 and 0. But I believe there's not exactly a problem you write it as decimals. Okay? So with that said, theta here will be equal to, let me take a look, 0.55357. Yes, 0.55357. Actually, I left the derivative as is and put it into my graphing calculator to get my 0. That way it was easier for me to do the second part. Okay, that's actually pretty solid. It's also a 100% valid way of doing it, actually. Okay, so my apologies, maybe I'm revolving through like very hard ways of doing the question. It was actually pretty straightforward. But yes, my good friend Alpha here is right. Okay, another way of just going a little even more straightforward. Sorry, this is how I solve the questions. I break it down maybe a little too much. You can do 4 cosine of 2x, as I mentioned. It's just for us to like get a nicer, prettier set of numbers than just the polar curve. Minus 2 sine of 2x. Okay, and then you take a look at, well, when is this equal 0? And you can actually take a look at that right here. Okay, 0.55357. Okay, so exact same value. Thank you all for that little slightly faster way of solving this question. My apologies if I made it a little complex for you fellows watching after the live or right now live. Okay, but yes, this will be our nice looking angle. Okay, for me, I will usually not risk it and just stay with this angle. Maybe you guys want to round it. I'm not quite sure if you still get points when you round it. I believe so. Okay, shouldn't be that many problems, but I'm not quite sure. So, number 2 says, use a derivative test to determine whether the critical point in is the location of a relative minimum, maximum, or neither for R. Oh, this one's actually a pretty good one. So here, you usually just go for your classical approaches of first derivative test or second derivative test. Okay? So usually, the way I will do this, okay, is you put your angle, right, in a nice little sine chart. So this is my angle, theta equals 0.55357. And then you look at some angles in between, right? You get some angles in between. So for this one specifically, okay, you already have your R prime of theta. Okay, you just got to be a little more careful, right, when figuring out these derivatives, because you have to take a look at the sine, right, the sine of your derivative on both sides, right, on your left and to the right of your angle, right, without going too far. So for example, here the values I will personally use, okay, are x equals pi over 2, okay, and 0. Okay, they actually kind of get very considerably in between, right? They don't go too far beyond. You want to make sure, they are slightly closer together, okay? And then you take a look at the signs there. So for example, if I use theta equals 0 here and theta equals pi over 2 here, you may notice that r prime of theta, well, r prime of 0 specifically, sorry, r prime of 0 here, if you go back to the decimals here, it actually goes above the curve. Right, here's 0.55, right at 0, okay, at theta equals 0, it actually equals 4. So that is greater than zeros, okay? So here is positive, okay? At theta equals 0, r prime of theta is positive, but then afterwards for pi over 2, okay, you look back here, pi over 2 it actually equals negative 4. So here, r prime of pi over 2 is less than 0. That's negative. Okay, and through this sign chart approach and knowing, what happens when you go from a positive derivative to a negative derivative. Okay, in this case, think about it this way. Let's say we had a curve that has a positive slope of a tangent line first and then goes to a negative tangent line. You can see there that therefore we actually have a maximum. Okay, so I believe using the derivative test and the sign chart approach or a table, because they also accept tables. Usually they're actually show the answers a little more often in terms of tables. You can tell them the critical point is a relative maximum. Okay, so this will be relative max. Okay, well, I think I got everything right according to stream except part 4. It's completely fine. They must have still did an excellent job. So yes, just as a brief thing, the table format, which is usually how they show it in the solutions, for each year, they kind of look like this, right? You have your theta, you have your r prime of theta, and you look at values in between. So here you'll have your 0.55357. Here you'll have pi over 2. And here you'll have 0. Okay? And I have those a few points. You look at the stuff in the calculator. Maybe, but hopefully you still got, those nice partial points, and we didn't go through that much trouble. So this one, you can stay at 0. Well, that was 4. For pi over 2 was negative 4. And for this guy, I actually don't remember the amount. Sorry about that. Oh, yeah, of course, it was 0. Oh, my. Silly me. But yes, this essentially is something you will be able to do and explain, right? Maybe in terms of words, right? Due to the, your nice sign chart. It had a different name, but I kind of forgot about it. Nice to our nice sign chart and the values of our derivatives being positive and going from positive to negative, then now we know, okay, that our nice derivative, okay, is now, our nice critical point here is a relative maximum. Okay, let me actually highlight that again because I always forget of highlighting the C thing. Right, so here let me actually write the two parts of the question. This was part I, this was part II. Okay, there we go. Not bad, not bad, not bad. Going back, now we have part D. Oh, okay, part D's. Now it's one of my favorites, but back then when I took it, I hated it. I disliked it a lot. I didn't like it quite a lot. Okay? So what does part D actually tell us? Part D asks for the average distance from the origin to a point on the polar curve. And I can see Alpha is actually wondering, wait, average value, something as simple as average value. Yes, it's actually pretty simple. But back then, I didn't have it quite well on my mind. I had different other calculus and personal stuff in my mind, so I wasn't able to remember the average value part. But it's pretty interesting and kind of straightforward. Because when they ask you for the average distance from the origin to a point in the polar curve, through this r of theta, between pi over 2 and pi, okay? Remember what I mentioned previously when just starting the BC FRQ number 2. The integral of r of theta, d theta, is not your area, but your accumulated radius. Okay? Now there's another little thing that I also mentioned just in a note, didn't directly mention it on the video, but I did show a little note on it when it's showing the manual, that the average value of a function, right, the average value of a function is the exact same thing as 1 over b minus a of the integral of a to b of r in this case, d theta. Okay, in this specific example, r of theta d theta, or f of x dx could work the exact same way. So the average value of a function, right, the mean value theorem and others, it's basically just 1 over top boundary minus lower boundary times the integral, okay, from a to b of r of theta or f of x, etc. So that's how you find the average value of a function. And because here we had an accumulated radius, and here they asked us for an average distance, the thing may seem a little odd at first, because they say average distance from the origin to a point. It's like, wait a minute, what? Distance from origin to a point? But if you think it a little more cold-minded, you remember, oh wait, the distance from the origin to any point in the polar curve is just the radius of the polar curve. That's just the output of the polar curve. It's nothing too out of the ordinary. Okay? This is the distance slash radius. So what they're basically asking you is, I get the average of the accumulated radius. Okay? As simple as that. It's pretty straightforward, actually. So with that in mind, the way for us to solve part D, okay, here in our calculations, will be the average distance. You essentially just write the integral. Okay, and here you gotta be careful because here they set up different boundaries. I see. I would you where my teacher see as part D was easy. Exactly. Part D is actually pretty straightforward. Okay, and also thank you for the compliment, Davis. I really appreciate it. Here I was mentioning, be careful with the boundaries, okay? Because here, previously we're working with 0 to pi over 2 or 0 to pi, but here we're working from pi over 2 to pi. So those are your A and B boundaries. So first, 1 over, okay, this is your A, this is your B. You go pi minus pi over 2. And then you go integral from pi over 2 to pi of your R of theta, d theta. This, my friend, is how you get part D right. Okay, now of course maybe you have to completely like mention the whole process, right? Not just the simple calculations. Ooh, that worked well. Okay, let me just copy this thing because I'm just gonna make it right under here. Oh, sorry. There we go. Better. So here I'm just gonna copy this thing. So because now instead of writing R theta, only R theta, I'm gonna write the full actual function. Okay, it looks like 3 plus 2 sine of 2 theta plus cosine of 2 theta, okay, d theta. Then it says, I was thinking I had to convert to parametric, then find the magnitude. Interesting perspective, but technically this is the slightly faster and nicer way to do it, okay? But still, I believe you still did a great job. That could be an approach, but the faster approach will be to thinking of the distance from the origin to the point of the polar curve. It's just essentially the radius, right? It's essentially the output that you get from a polar curve, okay? So doing this, performing this calculation, okay, let me actually put it in decimals, okay? I already, this is the thing I was talking about, okay? When you write your function, write your R theta directly, it becomes way easier to like plug in stuff on decimals, okay? So for example here, this was really for the area, for the average distance, okay? You go 1 over pi minus pi over 2, okay? Of the integral from pi over 2 all the way to pi, all the way to pi of R of theta, d theta. There we go. And as you may notice here, this one is still properly written from my understanding, yes. This is the average distance from the origin to a point. Okay, the average radius, if you want to call it also that way. Okay, so for D, the answer, okay, distance, so average distance equals 1.727. Well, no, yeah, technically yes, that's what I'll run it. 1.727. Okay, 1.7267. No, please, no joke about 67 in the comments, ladies and gentlemen. But yes, 1.727. All right, decimals. My apologies. Yes, you run out of time. It's completely fine though. It's completely fine. This is essentially how you will break down part D of question 2 for the BC FRQ. Okay, so this is the average distance, and this overall, so you will solve your second FRQ for the BC version. Okay, so let me again use my export tool, say FRQ to BC. Okay, export that. Nice. Whew. Oh man, sorry, I need a little bit of air. All right, pretty good, not bad. Let me also drink a little bit of water. All right, fellas, we're gonna be here for a little while, because now after this, okay, officially we have finished a total of 3 questions so far. We've finished the AB FRQ 1, AB FRQ 2, and BC FRQ 2. Okay, the ones that will follow, okay, the ones that will follow from now on are AB and BC. Okay, they're the exact same questions. 3 and 4. Okay, so 3 and 4. Let me take these guys out. Unfortunately, I believe also, yeah, I accidentally deleted my AB worksheet. My apologies. Let me just bring it back. Much better. And keep this guy also hidden. Not bad. So for AB, skip a little. I already solved that question. Okay, so now we're jumping into actual part B of our FRQs. Okay, for both AB and BC. So let me actually change that title. We have AB/BC FRQ number 3. Okay? Oh man, I believe I'm gonna run out of voice. Hopefully not. Let me be a little careful with the voice. So, a pie is taken from a hot oven and put on a table. The internal temperature of the pie at time t minutes can be modeled by the function h that satisfies the differential equation dh dt equals -1/15 of h minus 20. H of t is measured in degrees Celsius, and h of 0 equals 75. So that's already an initial condition, okay? Something also mentioned in the differential equations part of the video, initial condition. So not bad at all. So I already know for a fact that this is going to be a question about differential equations. Okay, you guys may have guessed it because of dH/dt or stuff of sorts. Okay? So this is actually pretty cool. I think for this one, I just sold on part A because I didn't know how I was supposed to write that FRQ. Fair enough. Completely fair enough. So let's take a look at what part A actually tells us. So, explain why the following could not be a slope field for the differential equation dH dt equals -1/15 of h minus 20. Okay, this is actually pretty interesting. So for this one, okay, we're going to go for a similar approach to what I mentioned in the video. Let's take a look at what quadrant we are in right now. Okay, the quadrant we are in just right now, okay, is quadrant number 1. And in quadrant 1, usually I will say x and y are positive, but in this case, we don't have x and y, we have h and t. Okay? So t is greater than 0, h is greater than 0. Okay? Which is not bad at all. Okay? It's actually pretty straightforward, etc., etc. Now, here's the problem with that. If we think that h, okay, h here is going to be greater than 0 in this quadrant, okay, what happens when h here goes a little bigger than 20? What's going to happen there? Let's take a look. If we write dH dt, we equal this to -1/15. Okay, let me actually write this little line where h equals, well, h is greater than 20. Let's call it that way. Okay, don't judge my notation. This is a way to, you know, explain what happens when h goes larger than 20. Okay, if h goes larger than 20, then this here right here, this thing right here, is not going to be 0. And right, if h was equal to 20, that will be 0. But when h goes above 20, then this is positive. Okay? And because that's positive, I mean, we're multiplying here for a negative. Okay? We're multiplying here for a negative. That means that dH dt, when h is greater than 20, must be negative. However, you may notice that in this nice slope field, okay, which is pretty nice, well drawn, we don't have a single negative slope. We don't have a single instance where dH dt is negative. You don't see any slope that goes downwards like this. Okay, you don't see stuff that looks like this. No. All of them are positive, which is a problem. Okay, because you can see here that our nice boundary, okay, if you wanted to call it this way, this is h equals 30. Okay, let's say that h20 is around here. Okay, h equals 20. According to the actual logic of the differential equation, above h equals 20, right, like h equals 30, 40, 50, 60, 70, above all of that, these slopes should be going like this, right? They should be negative. There should be a negative slope. But you can see how all these slopes in the thing above 20, right, in the slope field when h above 20, they're positive. So the way I will explain it, maybe I don't know if I will get 100% full marks, but this is the most straightforward explanation I can think about, is dHdt when h is greater than 20 must be negative. However, the slope field shows positive slopes when h is greater than 20, which does not align with the differential equation. There we go. So this is the way I will answer part A. Okay? I may or may not get full marks for that one, but that's an explanation. That's the best explanation I can think about of why this slope field cannot be a representation for the differential equation. Okay? That's how I will do it. Let's jump to part B. Part B says, find the slope of the line tangent to the graph of h at time t equals 0. Well, this is going to be interesting. What they're asking us here, okay, the slope of the line tangent to the graph of h, which is actually pretty straightforward, because the slope to the line tangent to this graph is just dh dt. But they explicitly tell you at time t equals 0. Now, wait a minute. This differential equation doesn't have time. It has h. It has value h. In this case is, wait. Oh, I just realized it's about a pi. That's kind of funny. Oh yeah, here we don't have time in the differential equation. We're having it in terms of h, right? In terms of, I believe, yes, temperature. So, with that in mind, what do we have to do? Well, we have to think of what happens when we have h of 0, right? When we have h of t, we have h of t when, what's h of 0? What's h of 0? Well, we can actually look back into the equation, and they tell us that through an initial condition. H of 0 equals 75. Okay? H of 0 equals 75, which means that for us to solve this, we just have to plug in the value of h of 0 equals 75. There we go. So the same thing as saying dh dt at h equals 75, which now is, okay, let me actually do my calculations carefully, negative 1 over 15 times 75, okay, h minus 20, okay, you may see here as h minus 20, so here we're writing 75 minus 20, 75 minus 20, and let's actually compute that little by little. Let me bring this thing to this side a little more so we can actually have some space to write, right, because now we don't have a calculator anymore, we have to actually solve this by hand, okay? 75 minus 20, that just equals 55. So this thing I'm saying negative 1 over 15 times 55. So now you're figuring out, okay, well, what's 55? Well, yeah, negative 55 over 15. Okay? So usually, here the most straightforward way of approaching this is just common factors on top and bottom, right? Or I believe I was called, I kind of forgot the name of the thing, but it was like least common factor. Actually, no, that's not it. That's not it. My fault. No, essentially the factor between 55 and 15, right? The greatest common factor. And that, I believe, will be 5, right? Or at least we can start with 5 and then keep going. So 55 divided by 5, okay? 55 divided by 5, that's just 11. Over 15, well, and 15 divided by 5 is just 3. And there we have it. We have our nice value for the slope of the line tangent to the graph of h. It's 11 over 3. Now here, they don't exactly ask you for units. They just ask you for the slope. So just giving this as a final answer is more than enough. Okay? So let me actually label that too as part B. Nice, pretty good. Let me drink a little more water. I think I may need it. The water is gone, ladies and gentlemen. I may have to get a water later. Ooh, sorry about that. So, here, it can, part C, it can be shown that we have the second derivative of h in terms of t equals 1 over 225 times h minus 20. And the line tangent to the graph, wait, I wrote a very similar FRQ for part A, but I thought I'll get points because of how I wrote it. It's completely fine. So, second derivative of h in terms of t is 1 over 225 times h minus 20. They say the line tangent to the graph of h at time t equals 0 is used to approximate h of 5. Okay, interesting. So what does that exactly mean? Okay, they're essentially telling you the line tangent to the graph of h, so dh dt, dh dt at t equals 0, basically what we just saw, like the slope, that's used to approximate h of 5, the internal temperature of the pie at time t equals 5. Is this approximation an overestimate or an underestimate for the actual value of h of 5? And give a reason for your answer. Now you may wonder, well, how do we figure if this is an over and underestimate? Well, the secret here is this nice gentleman right here. d squared h over dt squared. If you may recall, a second derivative usually represents the concavity, okay, of a curve. Concavity of a curve. Because it talks about the concavity, all right, because it talks about the concavity, we're going to use this guy to realize, all right, is our tangent line going to be an over or an underestimate? But how can we do that? Okay, well, we have to know to see if the thing it's a concave up or concave down. Because that helps us realize, let's say I had a tangent line right around here. Let's say that this is my tangent line at t equals 0. Okay? You may notice, okay, you may notice that one of them is, well, sometimes, okay, there's going to be instances where the thing is over the curve and instances where the thing is going to be under the curve. So, for example, here, okay, in the max scenario, well, no, sorry, in the concave down scenario, my approximation, right, my linear approximation, some people call it linearization, okay, approximation is overestimate. It's an overestimate because, as you can see, it's over the actual curve. Okay? But in the other instance, for concave up, it's an underestimate. Approximation, underestimate. So we're going to figure that out in just a second. But actually, we can actually go kind of straightforward with this. Because they don't tell us solve for the actual approximation. They tell you, is this approximation an over and underestimate? Well, let's go straightforward and figure it out. As I mentioned previously, this thing is in terms of h, not in terms of t. We have to use the value h of 0 equals 75 to also solve part C. Okay, so we're going to use, actually, yes, no, we're going to keep that there. I'm going to do this slightly more to this side. With the t squared at h equals 75 equals, we'll have 1 over 225, okay, of 75 minus 20. Okay, h minus 20, 75 minus 20. As we mentioned previously, 75 minus 20 is 55, which means that this whole thing is 55 over 225. Now we can keep it this way and state how this thing is greater than 0. It's positive. It's a positive number. So little by little, let's start writing the thing down. Okay? Since the h dt squared at t equals 0 is positive, okay, since the thing is positive, the curve h at t, oh wait, sorry, not at t equals 0, my apologies, t equals 5. Ooh, that was actually a pretty bad one. Okay, I just realized my very bad mess up. My apologies, ladies and gentlemen. But it's all right. Because, going back to this thing. So this thing that I'm figuring out just right now, this is at t equals 0. That was my bad. My apologies, ladies and gentlemen. So here we actually have to work with t equals 5. Okay? But how do we actually figure out, well, how do we figure out t equals 5? Okay? They don't actually give us the value h of 5 anywhere. Well, that's because we actually have to solve for it. Unfortunately, that time has come. We have to use separation of variables to solve for this value t equals 5. So let's go for it. Let's remember our dh dt equals negative 1 over 15 of h minus 20. Okay? H minus 20. Let me actually kind of take a look at... Actually, wait. Let me take a look at something because I may actually not be as wrong as I think. Let me actually carefully take a look at this question a little slower. They say the concavity and then the line... Okay, never mind. I'm not wrong. I'm not quite wrong because you do use the line tangent at t equals 0 to approximate h of 5. Okay? That's to approximate h of 5. Internal temperature at t equals 5. So you do have to use... Okay? You do have to use the previous values of h that we worked with. So let me actually bring them back. My apologies if that was a double confusion. But yes, you gotta be a little careful with these values that you're figuring out. Because now, okay, we can actually kind of go a little more straightforward and say, okay, are we concave up or are we concave down? Okay? But according to this, since d squared h over dt squared at t equals 0 is positive, the curve h... Okay, the curve h at t equals 0 is concave up. Okay, remember, if your second derivative is positive, we're talking about concave up. If it's negative, it's concave down. Okay? Since the second derivative at t equals 0 is positive, the curve h is concave up. And the linear... Okay, the linear approximation would go under the curve okay, the linear approximation will go under the curve as we saw in this scenario. Okay, that's how linear approximation kind of look like. Okay, it will go under the curve. Okay, and you can even prove that. Oh, actually, I almost messed up something. Okay, I almost messed up something. This thing right here, this value is negative 11 over 3. My apologies. Keep that in mind, right? That's negative 11 over 3. Okay, going back. And the linear approximation will go under the curve, which means the approximation of h of 5 is an underestimate. Let me go a little to the side. There we go. Underestimate. All right, not bad. So yes, that would be the approximation of h of 5 is an underestimate. To surprise of everybody. Whew, I believe I performed this question properly. We took a look at the line tangent. We took a look at the approximation h of 5, the internal temperature. Yes, I believe this will be correct. Okay? So, because we use that factor and all those stuff, and the tangent line being under the curve, the approximation of h of 5 is an underestimate. Not bad. Now, for the second one, we actually do have to use separation of variables. Sorry, guys, we actually didn't save ourselves from separation of variables. It's still here. Okay? So let's tackle it. So use separation of variables to find an expression for h of t, the particular solution to a given differential equation with initial condition h of 0 75 equals 75. I mentioned previously was an initial condition. So let's actually write down little by little dh dt. Negative 1 over 15 times h minus 20. Not bad, not bad, not bad. So with this in mind, the first step, we have to send, it's going to split our dh and our dt. So dh, so here technically we'll have to multiply by dt on both sides. So we have dh equals negative 1 over 15 h minus 20 dt. Okay, and then we can divide this h part, right, this h minus 20 thing, by both sides. So you have h minus 20, h minus 20. Okay, so now our thing is going to look like this. dh over h minus 20 equals negative 1 over 15 times dt. And now it's the step for us to integrate both sides. By integrating both sides, okay, this thing right here, okay, we actually people will usually go for the u sub approach, right? Say u equals h minus 20. Then turns out du is the exact same thing as 1 dh. So you can just integrate this thing as 1 over u du. So far, the IBT question that I got wrong. Totally fine. Alphabet, you still did great, likely in the other questions. Going back to this thing, when you do u sub, you have 1 over u. The integral of 1 over u is natural log of the absolute value of u, or in this case, h minus 20. Okay, actually, let me kind of show that thing as a step, just to not confuse people. Natural log of the absolute value, h minus 20. Okay? Because this h doesn't have anything like a 2 or a negative 2 or a negative 3 or stuff of sorts, I will usually just go straight forward from this step to this step. But if you want to go safer approach, this is also completely valid. Okay? And for the other guy, this is in terms of t. And because this is just a constant, we can actually just write this thing. And actually, let me be careful. Because here, in this one, I kind of skipped the c, but here we do have to write c. Okay, this is an indefinite integral. For separation of variables, we usually just write c to one side. Okay, we don't write on both sides. We're focusing on one side of c. Okay, so here we have negative 1 over 15. Okay, we integrate that. That's negative t over 15, or negative 1 over 15 times t plus c. Okay, let me actually kind of write that t like this, and this. There we go. Better, so we don't confuse both. So we're actually we're doing a pretty good job right now so far. So with this in mind, okay, with this in mind, now it's time for us to use our initial condition. So let's do it. Our initial condition says that when t equals 0, h equals 75. So technically, the natural log of 75 minus 20, that's just natural log of 55, is the exact same of negative 1 over 15 times 0, right, t equals 0, plus c, which means that c is just natural log of 55. Okay? Pretty good. Now, with this in mind, okay, with this in mind, we can proceed with the rest of our nice equations by plugging the c back into this baby right here, this guy right here, and write. And actually, this with a different color. Natural log of h minus 20 equals negative 1 over 15. Let me actually write a negative t over 15, just to kind of save a little bit of time. Okay, it's the exact same thing as negative 1 over 15 times t. This plus natural log of 55. Okay, we're getting closer and closer because we have a log here and the h is right here. We're trying to solve for h here. Then we will usually just go for exponential logarithmic transition, right? So we make this thing go from logarithmic to exponential, which means the thing looks like e, okay, because this thing is just log base e, natural log is just log base e. We have e to the negative t over 15 plus natural log of 55, right? So it's just e to this thing right here, this side of the equation, equals h minus 20. And last but not least, the way for us to solve for h of t is just adding 20 on both sides, plus 20, which means that h of t equals 20 plus, okay, you don't have to get the c value. You can just make the entire right part as the power of e and make e to the c as 55. That is true, okay? That is 100% true. What Alpha just said right now is certified hood classic. Sorry. But yes, that's right. You don't have to get the c value 100%, but as long as you actually also remember how you go from how you go from differential equation for exponential growth or exponential decay to your actual function. You can also do that, but I believe in this case they specifically say separation of variables. So what I guess alpha is means, okay, is making just the entire right of power of e. So this thing right here, okay. But here's the cool thing, because you have natural log of 55 here. You can actually send this thing down, because if you think to yourself, well, e to the natural log of 55, that's essentially just saying 55. So the actual answer for this will be 55 times e to the negative t over 15. Okay? If you guys wonder why I was able to write that 55 in front, it's just because if I grab the e part, so e to the negative t over 15 plus natural log of 55, because here I'm adding my exponents, right? I can break this down into e to the negative t over 15 times e to the natural log of 55, which is the exact same thing as what I mentioned previously. That's how we get to this thing right here. Okay, so just for the people in the stream or after the stream, don't get too confused. That's essentially the logic that you do behind all of this. Okay, nice. So, whew, that was a lot. That was plenty of stuff to do in a single question number 3. But at least we were able to walk through it properly, nicely, and easy. Let's take a look at the rest of this stuff. So, again, let me take a screenshot of this. The screenshot may not be so clear, that's why I do the exporting. Right, that's why I like to export the thing. So we export that, not bad. We also export it here. So this is just FRQ number 3. Excellent. Oh man, I do need a little more water. Ladies and gentlemen, wait for me just a second. I'm gonna go for another bottle of water. I am back again, ladies and gentlemen. Whew, man, I really need. I don't know if you guys want to perform a brief pause. I personally don't want to, because we have concurrent viewers that want to get to their answer. Okay. But I also have a couple of limitations, and that's being a human and having a voice that's not trained for talking for so long. But I might do my best to finish all these questions while not losing my voice in the process, okay? Let's go for it. So for these guys, take this out. This is gone. And you're gone too. Alright, so we have our nice worksheet here. We can actually skip just to the next page, number 4. Oh man, this looks like such an easier question. Great, wonderful. This is what I like to see, ladies and gentlemen. So, let me show my hands a little. Let's take a look. Let f be a twice differentiable function on the closed interval from -4 to 4 with f of 2 equals 3. Not bad. And they give you the graph of f prime, the derivative of f. So, highlight this thing. This is not f of x. This is f prime of f of x. Okay, this is f prime of x. This is the derivative of our good friend f. Oh man, my throat hurts a little. My apologies, ladies and gentlemen. So, going back to this thing. For x greater than 0, the function g is defined by g of x equals f of x minus natural log of x. And find g prime of 2. Pretty simple, straightforward. We take the derivative of g of x. So, g prime of x equals. So, f of x, the derivative of that is just f prime of x. Minus natural log of x. The derivative of natural log will be 1 over x. And now we're able to compute g prime of 2. Right? So now it's just plugging in stuff. So g prime of 2 equals f prime of 2 minus 1 over 2. So let's look back. F prime of 2, if I go to x equals 2, okay, they already give me a point. Okay, then f prime of x equals 1.5. Not bad. So now we know that f prime of 2, okay, f prime of 2 equals 1.5. So we write 1.5, or also known as 3 over 2. Just write that there. 3 over 2 minus 1 over 2, which equals 2 over 2, or just 1. So g prime of 2 equals 1. There we go. Pretty nice, straightforward, and nice and easy. Thank God I wanted to take a look at one of these easier questions because my voice was being destroyed. Part B. Find all values of x on the open interval from 0 to 3 at which the graph of f has a point of inflection. I like this. I like this a lot. So, they ask, find all values of x on the open interval from 0 to 3. Okay? And they also ask for a point of inflection. We know that a point of inflection happens when f double prime of x, okay, so this, which determines concavity, equals 0, which means concavity changes. So looking at that, okay, they specifically tell us in intervals from 0 to 3. Okay? X intervals from x equals 0 to x equals 3. Okay? But here's the interesting thing. We don't have a function for f of x. And that may seem a little bit of trouble at first. But remember, okay, f prime of x and f double prime of x still behave like just one is a derivative of the other. Okay? Therefore, you can still use the logic of having a maximum, okay, having a maximum somewhere or a minimum somewhere, as finding an inflection point, okay? As if you would regularly find a maximum or a minimum. And what am I talking about? Well, if I have a horizontal tangent, okay, like here, for example, at 0.13, I have a horizontal tangent of my function f prime of x, which means that this is a point where f double prime of x equals 0. And if you notice, that's a unique actual vertical tangent that we have, horizontal tangent that we have in the whole interval. Okay? So you can actually give that as a reason for your answer. The point, well, yes. Yes, no, I'm going to write it as the point, so the point 1, 3, I believe. I could be wrong. Let me take a look real quick back. There we go. To point 1, 3 in f prime of x is the unique relative, and I'm not going to say maxima here. I have to be a little more broad. In this case, we're going to say relative extrema. Okay? In the interval (0 is less than x, which is less than 3. And because there's a relative extrema, okay, and you can see here this little nice trajectory, right? We're having an actual relative extrema. If you have a relative extrema, that means that your function, okay, your concavity here, well, your concavity here is changing, okay? In this case specifically, you have a maximum at f prime of x. If you have a maximum f prime of x, that means a critical point, okay, for f double prime of x, okay? Is unit level extension, okay? Therefore, f double prime of x has an inflection point at x equals 1. Okay? This is the way I will answer this question. Okay? Maybe I'm missing something. The point 1, 3 and f prime of x is the unique relative extrema in the interval from 0 to x to 3. Right? Because it has a relative extrema. Oh, sorry. because it has a relative extrema, okay, and maybe you can actually, even mention this too if you want to be a little more specific, okay? I would actually recommend you to, okay? Since x equals 1, well, since f prime of 1 is a relative extrema, f double prime, okay, f double prime of x goes from positive, well, and specifically maximum, okay, if you want to be a little even more specific, okay, f goes from positive to negative, and concavity changes. Okay? Therefore, f double prime of x has an inflection point at x equals 1. Now, I will recommend for these sort of questions, you don't have to like start yapping as much. You have to be very straightforward, but also have to understand what thing leads to the other, right? That's the thing behind give a reason for your answer. Okay? Give me a little minute. I still need to drink some water. Oh man, that hurt. Whew! So, part C. From -4 to 4, on what open intervals, if any, is the graph of f both increasing and concave down? So it's actually pretty good. I actually like this a lot. So, is the graph of f both increasing and concave up? So what do we have to actually break down from that? Well, f is increasing, which means f prime is positive, and f is concave down. So I'm actually just write a happy face. Well, sorry, a sad face. Or just write concave down and then the sad face. Right? There we go. Which means that f double prime is negative. So we're looking for instances where f prime is greater than 0 and f double prime is less than 0. Okay? And we can actually also break that down because we don't have the graph of f double prime of x, but we do have the one of f prime. And if we know that f double prime is less than 0, this also means that f prime is decreasing. Okay? F prime is decreasing. So that's essentially what we're looking for. We're looking for intervals where f prime is positive, but it's decreasing. Okay, so let's take a look at each of these segments, little by little. This one from -4 to -3, okay? From -4 to -3, f prime is decreasing, but it's negative, so that one doesn't count. From -3 to 1, okay, it actually increases the whole time, so we're not looking for that. From 1 to 2, we're starting to have some nice results. Okay, you may notice that from 1 to 2, okay, the thing is positive and it's going down. And it's just the exact same thing is going on from 2 to 3. Okay, so you can grab all that interval, okay? 1 is less than x, which is less than 3. That's already one of your intervals. And then the other part, well, here f prime is increasing, so that essentially doesn't count. Okay? So good. We already broke down all the parts that part C actually, needed. So, how do we actually put it into words? Well, we say, okay, increasing concave down. In the interval, okay, in the interval 1 to 3, okay, 1 is less than x, which is less than 3, okay, in the interval 1 is less than x, or which is less than 3, f prime is both positive and decreasing. which means our function f is both increasing and concave down. Now, I will recommend you write both these portions, right? These logic portions, right? Of, if f is increasing, f prime is positive, f is concave down, f double prime is negative, okay? And even write this stuff, because that's essentially actually giving a reason for the answer. If you said this, okay, you're not connecting a lot of stuff together, right? You're not actually, connecting the logic of certain parts of the question. You have to be very specific, okay? Both justification, explanations, giving the reason for the answer, etc. Oh man, sorry about that. All right. For negative 4 all the way to 4, find the value of x at which find the value of x at which f has an absolute minimum and the value of x at which f has an absolute maximum. So we have to find absolute minimum and absolute maximum. How do we do this? We always take a look at first the endpoints, so negative 4 and 4. So think about it. Try to think about it this way. Okay. Try to think about it this way. Let me actually write a table for this. Okay, write table. Nice, pretty good. So table x. This is f. We're talking about negative 4 and 4. Okay? We're talking about negative 4 and 4. And we're trying to, figure out the absolute minimum and maximum. Well, when we're talking about absolute minimum and maximum, we're not only taking a look at the endpoints, but also all critical points. So let's take a look at all critical points. As you may remember, critical points, or crit points, let me just write it that way. Crit points happen when f prime of x equals 0. Now let's take a look at where that actually happens. Okay? Where does that actually happen? Give me a minute. I need a little bit of water. Much better. Okay? So where does that actually happen? Well, we have a critical point at x equals negative 2. Let me actually highlight it with red. X equals negative 2 has a critical point, right? And x equals 3. X equals 3 is another critical point. So interesting activity around here. Let's take a look at it little by little. Sorry, give me a minute. My apologies if I'm drinking too much water. I just needed to actually survive and not, run out of voice. Windows security, I don't care. Or hopefully I don't have to care. You never know. Whew. So taking a look at this, okay. Oh, and let me actually not forget something very important. One piece of information they give you is f2 equals 3. Okay, you may want to use that as one of the things that you must use for your reasoning through the table. Okay, so x equals 2, f of x equals 3. Okay, and then we also highlight all the critical points besides that given one, because the given one is very important. We have negative 2, we have 3, and we have 4. Okay, now what's going on there? Something you may notice, okay, something you may notice is that right after x equals 2, okay, right after x equals 2, between 2 and 3 and 3 and 4, we only have positive area, okay? F prime of x is above x, the x axis, which means that all this is positive area, okay? Let me actually do it with a lighter color, slightly better. Nice. So all this positive area. Okay? We have some nice, neat, positive area. And the exact same thing happens between negative 2 and 2. Okay? You still have some plenty of positive area in all of those guys. Okay? So you, little by little, you may kind of get the catch of what we're trying to do here. We're trying to take a look at all the areas, okay, that we were adding up at the end, right, from interval to interval, usually going from left to right, to figure out, okay, which one of these is an actual absolute minimum or maximum, okay? So give me just a minute because we're having a I'm trying to reason a little bit of my way through these questions because we do get only one fixed value, okay, of my function f. And I'm just trying to carefully take a look at the rest of the information that we're required to have. Okay, I think I see what's going on. Whew! So, here's the thing. Going from left to right, not only you have stuff, more positive area around here. Okay, so let me just do it this way, a little more pretty. You have more positive area between -2 and 3, which means that whatever value you started with at -2, it kept increasing. Okay? Whatever value you started at -2, it kept increasing and increasing and increasing and increasing. Okay? Which means that likely the highest value that you can get, okay, the highest output f that you can get is at 4. Okay? So that's just, we're not using the table just yet. I just want to give the idea of the area thing that's going on here. Okay? So, when you start at x equals -2 forward, all the things that you have, right, from -2 to 4, that's positive area. Which means, okay, which means that even at 3 here, the number just kept increasing. Okay, it didn't stop increasing at all. It didn't stop increasing until 4, which is, the last part of our interval. And what does that mean? Well, that means that 4 here, because all that positive area from -2 to 4, that's the highest value that we can think of. Okay, the absolute maximum that we can think of. Okay? But then you may wonder, well, then in that case, what's the absolute minimum? Okay? What's the absolute minimum? What's the absolute minimum? Okay, and that's something kind of cool that we can actually kind of reason through. Because, okay, let me actually get, man, I'm sorry, stream, I still need water because I've been streaming for 2 hours and 30 minutes. And talking for too long. Going back. If we're reasoning, okay, our way through this, we know that 4 will be our absolute maximum, okay? Because after that value of f of 2, well, even after the value of -2, all of our area is positive area, which means that all of that area here, okay, that's the accumulation. That's accumulation that's counted up for my function f of x, okay? Which means that everything after x equals -2 is positive area, and the highest value that we're getting, okay, because all this positive area is accumulation, the highest value that we're getting is at x equals 4, okay? So that's already the absolute maximum, okay? That's already the absolute maximum. Now, what happens when we're trying to deal, okay? What happens when we try to deal with the most, like the lowest value, the absolute minimum, okay? The lowest of the lowest values. There, you have to now think about what happens before that. What happens when you have negative area, okay? What happens when you have negative area, okay? When you have negative area, okay, let me actually still drink some water. When you have negative area, now you're going slightly down, right? Your function is now going a little more downwards. So think about your function at x equals -2, okay? If you go a little before that, right, at x equals 4, then you actually lost some value, right? Your displacement was now, well, technically your accumulation was now negative, okay? Because your accumulation is now negative, okay? Because your accumulation is now negative, then that means that f of x decreased, okay? F of x decreased in that little interval, okay? Now, let me take a look at this carefully, because the positive area, the absolute maximum is fine. Now, when you look back, right, f of x decreased. And you may notice, ooh, sorry. Ooh, sorry about that. So, you may notice that not only that, but then our -2s and our -3s also account for specific ways of analyzing our maximum or minimum. Like for example, the -2 right here, okay, and sorry if I didn't mention this previously, this -2 went from a maximum, okay, well, sorry, not whatever maximum, it went from negative, right, from f prime being negative to f prime being positive. What does that actually mean? Okay, that means that -2 here is a relative minimum, okay? And 3, even though x equals 3 touch the x-axis and f prime of x is indeed 0 there, it didn't change signs, okay? At x equals 3, f prime doesn't change signs. It stays above the x-axis at all times. Therefore, x equals 3 is neither, okay? That's how you can also you know, go through the reasoning of why x equals 4 is our absolute maximum, okay? Now, -2, that's a relative minimum. What happened before -2? Okay? Well, actually, give me a minute. What happened before -2? Well, here, because -2 is a relative minimum, whatever, even if this part decrease, okay, even if this function part decrease, and you can even imagine it in terms of the axes, you can think of from -4, okay, x equals -4 to -2. Maybe your function went like this, okay? Your function went like this. There was negative accumulation, and also because your derivative there, right, from x equals -4 to x equals -2, your derivative is negative. Therefore, your function is decreasing. But then you hit that minimum point and then start going up, okay? And then you could go up in many different ways, but we know that because, okay, after x equals -2, then your function is, well, the derivative of your function, f prime of x, is positive, then you know you're always increasing. Then, okay, because of that, you know that x equals -2 is actually the lowest point you can hit, okay? X equals -2 is the absolute, okay, absolute minimum, okay? Now, chat, you may need to give me a second. I have to go to the bathroom. I'll be right back to keep going with these FRQs. Chad, we have returned. Oh, brother. Sorry for that. It took a little while. Whew. Oh, man. So, going back to this thing. Because we saw, okay, and maybe you don't want to use the accumulation as part of your answer. That I completely understand, okay? If you want to go a little more simple, then the best way to put it in words, okay, is that from -4 is less than x, which is less than 2, f prime was negative, and f was decreasing. From x equal, -2, not 2, from -2, okay. From x, from -2 is less than x, which is less than 4, f prime is positive, and f was increasing. Okay, and f was increasing. Okay, so maybe I have to move this to a slightly different space to have a little more space for writing. Much better. So now f was increasing. I just also realized that it didn't label the things, so let me actually also do that very quickly. This is part A, this is part B, this is part C. So from -4 to x to -2, f prime was negative, f was decreasing. -2 to 4, f prime is positive, f is increasing. Whew. From there, x equals -2 becomes the lowest, well, the absolute minimum, and maybe technically not x equals -2, but f prime, well, sorry, f of -2. Okay, f -2 becomes the absolute minimum at x equals -2. Okay, and then you start writing y 4 is your absolute maximum. From, okay, or you can even mention how from at, or because f of 2 equals 3, and from 2 to 4, 2 is less than x less than 4, f prime is increasing. Or technically, well, here's the thing. The reason of why here, why x equals 4 is your absolute maximum, is because from -2 all the way to 4, okay, your function f of prime doesn't stop, well, being positive, right? It's always positive. Okay? And what's going on there? Technically, okay, let me actually take this out for a minute because I need to like think little by little of the things that I'm mentioning, right? What I'm showing to you. So going back to this nice color. Function master, we're not this specific. Yeah, that's true. That I feel it's kind of hard to be very specific with some of these questions. Okay. So here is the thing. When you mention that from -2 to 4, f prime is positive, f was increasing. Okay. Since f does not stop or keeps increasing, from -2 is less than x, which is less than 4, okay, the absolute maximum of f is reached. Oh, yes, I believe, yeah, reached at x equals 4, right? Because starting at x equals -2, after that, you don't stop increasing, right? You keep increasing over and over, you keep increasing by a lot, okay? And before that, you were just decreasing a little, which means that at the end of the day, x is your absolute minimum, the lowest value that you can get, and after that, you just get an absolute maximum at the very, very end point, right? X equals 4. Oh man, that took a while. My apologies, people from the chat, if this one looked a little less pretty. Okay, this one was a little harder to actually understand from my part. I was just getting a little confused. A little confused about the wording of the questions. Okay, but this essentially is the basics that you will need to actually answer question 4 in the FRQs. So let me, and I also realized, oh man, I realized I didn't switch this FRQ. I knew I will forget the FRQ F4 number, but it's alright. It's okay. So let me just take a screenshot of this and export it. Just give me a bit of a second, ladies and gentlemen. Export PDF. FRQ4. Woo, not bad. Alright, hopefully the next question is going to be a little simpler because I need my voice to recover a little. Let's take a look. Oh, yeah, it actually does look pretty simple. So, says a remote-controlled toy car moves back and forth along a straight path. Its velocity t is given by this function. V of t is feet per second in t seconds. Not bad. So here's the thing: v of t will be our rate. Okay, this is our rate. This is likely a position, velocity, acceleration question, which is not bad at all. So we're gonna go step by step. We can also notice it's a piecewise function, and this is the graph. This is how the graph looks for all of this thing. First, we have to find the acceleration of the car at time t equals 1. Pretty simple, pretty easy. So first, at t equals 1, we have to take a look at which one of these actually corresponds for v of t. In this case, this is this one. For 0 is less than or equal to t, which is less than or equal to 4. That's where t equals 1 falls in, which means that for part A, okay, a of t, let's first solve for a of t, at t equals 1 equals the derivative, right, b prime of t at t equals 1, which is 2 to the 4th. Oh, no, sorry. Well, so the derivative, okay, so v of t itself is 2 to the 4th minus 8 to the 3rd plus 16t to the squared. Okay? So I take the derivative of each of these. Derivative of t to the 4th, 4t cubed. Derivative of minus 8 times t cubed minus 8 times 3t squared. Okay, because of power rule. I actually use power rule on all these guys. And plus 16t squared, so 16 times 2t. Not bad. So this thing at the end looks like, actually no, yeah, 4t cubed minus 8 times 3, that's 24. T squared plus 16 times 2, that's 32t. And we solve for, okay, actually wait, yes, this is a of t, I'm correct. This is a of t. We solve for a of 1. Okay, a of 1 means 4 times 1 cubed minus 24 times 1 squared plus 32 times 1. And we simplify. Right, we have 4 minus 24, right, because you're just multiplying by 1 over and over, plus 32. So that 4 and 24, that's going to make up minus 20. Technically, this is just saying 32 minus 20, which is just 12. So there we go. A sub 1 here equals 12. Not bad. A sub 1 here equals 12. That's all the work that you need. Let's take a look at part B. Part B says, is the car speeding up or slowing down in time t equals 1? Interesting. So for this one, you actually have to remember something that I put in the video, right? Also just in the screen, I didn't exactly narrate it. Saying, if a of t and b of t have the same sign, then it's speeding up. But if a of t and b of t have different signs, it's slowing down. It's slowing down. Okay, so due to this, now we have to find, okay, we have to find out at t equals 1. Are these guys the exact same sign, or are they not? Which is good because we already found a sub 1. Well, no, it's not a sub 1, sorry. A of 1, okay? A of 1 is 12, which is positive. That's good. Let's take a look at v of 1. So if we try to value b of 1, we have v of 1 equals 1 to the 4th, which is 1 to the 4th, minus 8 times 1 cubed, plus 16 times 1 squared. Right, 1 to the 4th is just 1. 1 cubed is 1. 1 minus 8, plus 16. 1 squared is 1, plus 16. Okay? Pretty straightforward. Okay? 1 minus 8, that essentially is just negative 7, plus 16, that's just essentially 9. Pretty good. So we can see here that v of 1 is equal to 9. And I'm back. Excellent demos. Pretty good, pretty good, pretty good. And a sub 1, well, so a, what am I saying sub? And a of 1 equals 12. Both of them are positive. which means that the car is speeding up. The car is speeding up, ladies and gentlemen. Nice. Now here they ask us, find the distance in feet that the car traveled over the time interval from 0 to 4. Show the work that leads to your answer. Okay? Now you may ask, okay, this is the distance, okay, that the car traveled over time. This is total distance traveled. Now you may recall something. If you integrate, okay, integral of velocity equals displacement. But, okay, the integral of absolute value of velocity, also known as the integral of speed, that gets you the total distance traveled. Total distance traveled. So that specifically is what we're looking for from interval 0 to 4. So that's what we're going to do. The good thing is, okay, function v of t is properly defined, okay, from 0 all the way to 4, right? From t equals 0 to t equals 4, which is this polynomial that we already deal with in the last 2 questions. Okay? So what do we have to do here? What we have to do, okay, is just take the integral from 0 to 4 of the absolute value, okay, of t to the 4th, let me see if I remember it, minus 8t cubed plus 16t squared dt. I believe that's the correct one. Yes, it is. Let's go. So this thing right here will give you the distance traveled. Now here's the good thing. In the graph, you may notice, okay, that your velocity here is always positive, right? Your velocity here from 0 to 4, from x equals 0 to x equals 4, is positive. Therefore, okay, because it's positive, all of the displacement here, it's already, the distance traveled. We aren't going, different ways. That will be later on, by x equals 6, from x equals 6 to 12, when now it becomes negative. But here is completely positive. Okay, and because it's positive, usually the reason of why we use absolute values, okay, for finding total distance traveled, is because sometimes your velocity is going to go the other way, right? It's going to go in the negative direction, like this, okay, just like this. But here, because from x equals 0 to x equals to 4, all the thing is positive, we actually don't have to worry about it a lot, okay? We can go straight forward and say, is the exact same thing as the integral from 0 to 4 of t to the 4th minus 8t cubed plus 16t squared dt. Okay? Let me actually start solving that in this side. So, first let me just copy it really quickly. There we go. Copy this, paste it. Not what I'm talking about at all. Let's grab this thing specifically. There we go. Copy, paste. Yeah, thank you very much. So that's the integral we're trying to solve for right now. Let me go back to my pen. dt. So we're going to go step by step, right? First, let's actually figure out the integral. So right now, we're using reverse power rule, right? T to the 5th over 5, right? That's from t to the 4th. For this guy right here, it will be minus 8t to the 4th over 4. And then this guy, 16t squared, will be plus 16t cubed over 3. Okay? This guy right here, the 8 over 4, you can simplify it as just 2. Okay? And now, you use the property of your definite integral, right? The fundamental theorem of calculus. So you go from 0 to 4. The good thing is, at 0, all of these become 0, right? When t equals 0, all of these is 0. This is 0. This is 0, this is 0, because all of them are being multiplied by 0. So now you have to focus, okay, on 4, right? On 4 right here, on the evaluated value at 4. So we have 4 to the 5th over 5 minus 2 times 4 to the 4th plus 16 times 4 cubed over 3. Not bad, not bad. Now something kind of interesting that I believe I recall, from solving this in the past. You go back to the very, very beginning, and you may wonder, well, why am I going back to the beginning? Okay. If I remember correctly, you may have scratch work in the previous one's booklet. So here's the thing. I remember. Okay, here. That's the thing. That's the thing that I was looking for. Unless otherwise specified, answers, numeric or algebraic, need not be simplified. So what does that mean? That means that if you give this, to CollegeBoard, you got full marks. You don't worry about it. Okay? And technically I lied because we're still missing one little part about this. The units. Okay? Essentially you'll have to mention the units. Because they asked you their distance in feet that the car traveled. So you use right here, feet. You don't have to simplify this, but it's there. As long as you actually understand how to do the arithmetic, everything is excellent. Okay? So pretty good. For the last one, find the average velocity of the car over the interval 6 to 12. Not bad. It's actually pretty straightforward because here we already have our velocity, function, specifically from 6 to 12. I just went back through to see that I missed 3 part C because I was just thinking too much into log behavior. It happens. That's normal. It's completely fine. Let's keep going with these ones. So, for average velocity, you may have guessed it, we have to use the average value of a function. And that's what I just already did previously. I did 1 over b minus a of the integral, a to b, of some function f of x dx. Here specifically, we're going to be working with velocity in terms of t. So, first, we're talking about 6 to 12. So 1 over, right, this is my a, this is my b. So we have 12 minus 6. Integral from 6 to 12, pretty good, not bad so far, of v of t in that specific interval. And you can look back into your piecewise function and remember this thing right here, this thing right here is the interval, and this is how your function v of t behaves in that interval. So you want to make sure you integrate this. So going back to the thing, you have 10 cosine pi over 3 t, 10 cosine pi over 3 times t minus 10, I believe I read. Yes, minus 10. Perfect, pretty good. dt, don't forget the dt. By solving this is how you will find your pretty wonderful answer for the overall question, So first, as I mentioned, I'll recommend doing the integral part first. So for this, you can simplify it. 12 minus 6 is just 1 over 6. Times, and then you will do the fine part right in the inside of this huge parentheses. So little by little, first, we can actually take care of that 10 here by just saying negative 10t, which is pretty straightforward. And then this guy, when you integrate cosine, you may have remembered from my video, you can use the unit circle to remember how that integration goes. Here you're in cosine, here you're in sine, and here you're in negative cosine, and this is negative sine. When you integrate, you move counterclockwise. So that means that now we end up with sine. But wait just a minute. I have a pi over 3 inside of that thing. So quick shortcut. This will usually require u sub, for this thing right here. But because it's only one constant, the u sub at the end is just going to leave you by dividing this number, by your overall answer. So keep that in mind. Now the integral for this thing specifically will look like 10 sine of pi over 3t. And you multiply by the reciprocal of this, by the reciprocal of pi over 3, which looks a little like 3 over pi. Minus 10, let me bring that 10 a little more forward. That's negative 10t a little more forward. that didn't work like expected. Let me grab it now properly. Much better. Nice. So this is your actual integral, and you have to evaluate it from 6 to 10. Okay? Now, I gotta be kind of honest with you. Solving this thing by hand is gonna be painful. So I believe I'm going to leave this thing as it is. Okay? Maybe we can plug in the values. Okay, let's plug in the values. We're actually leaving it as it is. We have 1/6, back parentheses. So first, the evaluated integral at 10. So 3/pi times 10 sine of pi over 3, or times 10, so t equals 10, so that would be 10 pi over 3, minus 10 times 10, which is minus 100, minus, again, 3/pi, 3/pi times 10 sine, this case is 6, okay, 6t, t is equal to 6, so it'll be 6 pi over 3, or, let me just keep it as 6 pi over 3. Okay, you could simplify that as just pi over 2, if you wish. 6 pi over 3. Ooh, man, and a little more water. Well, not pi over 2, sorry, 2 pi. You can simplify that as 2 pi if you wish. And then minus 10 times 6, which is just minus 60. Oof, that's a lot of stuff to cover. So, for the love of the game, for this one, I will solve it. I will actually break it down. The other one was a little harder because of the exponentials, but for this one, I'm actually going to break it down for you. I can't say that without thinking about somebody breakdancing. So, first thing, greatest common factor. Actually, I don't know about that greatest common factor. Actually, no, yeah, we go count that. We count those. So, we have 1/6. Let's simplify these guys. We have 3/pi. Okay, we can also say, actually, no, let's keep it as 3/pi times 10. Actually, no, technically the 10 is also a common factor. So let me actually multiply this 10 and this 3 together. So 3 times 10 just becomes 30/pi. Okay, sine of 10 pi over 3. Then I want to subtract this guy just to make it a little simpler to actually look at. So minus, again, 30/pi. Pi of sine, not bad, of sine of 6 pi over 3, or in this case 2 pi. Perfect, we're doing a great job so far. And then we write the other guys. So we subtracted this guy, then this minus 100 stays minus 100, but we are subtracting a negative 60, which means we're actually adding the 60. Okay? We're actually adding the 60. So let's simplify stuff a little bit here. First, this sine of 2 pi is just 0, okay? So this thing just goes away, okay? Kind of cancels out. And then this guy, 10 pi over 3, so if I remember properly, okay, 10 pi over 3, you can break it down as 9 pi over 3 plus pi over 3. Okay, 9 pi over 3 plus pi over 3. 9 pi over 3 can just be written as 3 pi. Okay, this can just be written as 3 pi, which means that essentially we're just counting this as pi plus pi over 3. So we got to be careful in understanding where we're actually falling here. Pi over 3, remember, is 60 degrees. Okay, so the value for that will actually be sine of 10 pi over 3 because 10 pi over 3 ends up below the x-axis. Okay, then that'll be sine being negative. Okay, so technically here, the answer for this one is going to be sine of 10 pi over 3. Let me just write that carefully here. 10 pi over 3 is indeed negative square root of 3 over 2, if I recall properly. Okay, because this 3 pi just means one full turn and then one half turn, which leaves you at pi, and then you add pi over 3. So pi over 3 here is your reference angle. Therefore, you get the square root of 3 over 2. Yes, pretty good. Nice, nice, nice. And because you're below the x-axis, you have a negative square root of 3 over 2. Okay? Let's keep simplifying these things. So now we have 1/6. Okay, we know that it's negative square root of 3 over 2, so you have negative 30 square root of 3 over 2 pi. This you cancel it out, and negative 100 plus 60, which ends up being minus 40. This, I think I will leave it that way. The 30 over 6, you could simplify this as negative 5 square root of 3 over 2 pi. And then this guy, negative 40, you will end up with something that looks like negative 20 over 3. So minus 20 over 3. So I believe, okay, when you simplify this part and all that, that will be your answer for that very last question, right? Find the average velocity. Brother, each question just keeps getting harder and harder. This is not great, but that's how it is. So again, fellas, for this one, I think I will pass on the labeling what each part is. Actually, no, I don't think I will pass, because then it's kind of hard to actually realize where are we. So this is B, this is C, and this is D. All this work is in D. There we go. Man, that took a while. So, let's take a screenshot and export it. There we go. We go here, not there. We go export PDF. This is for the fifth one, AB. Okay, and again, I forgot to change the label. I mean, I almost forgetting about that label. I mean, so serious. Technically, right now, I might as well just change it to BC. Okay, FRQ BC. I'm always going to put like timestamps at the very end, right, when we finish the whole live. Going back to this thing. Not bad, not bad, not bad, not bad. Alright, pretty good. So that was saved. Save that, save that, save that. This thing is done. So now it's time for us to keep moving. So we deselect this and take all that. Now the good thing, what happened here? I don't know what that is. I guess it's just Zoom glitching out after so much calculus. So now we're going to move to the BC number 5. Okay? I believe it changed properly. Yes, BC FRQ number 5. Let's go back here. Not bad at all. So BC number 5, you may notice 4 is the same. 5 is different. Right, 5 is a different question. Let's take a look at it. So, whew, oh man, it's gonna take a little while. Sorry about that, chat. I'm being a little just a little exhausted. So, let f be the function defined by f of x equals the cube root of x minus 1. And let g be the function defined by g of x equals e to the negative 2x plus 4. These two intersect at the point 2, 1, right around here. Let R be the region bounded by the graph of f, the x-axis, and the vertical line x equals 2. Not bad, not bad. Okay, pretty straightforward stuff. So evaluate integral from 1 to 2 of f of x dx. Let's do that. So for part A, integral from 1 to 2 of, in this case we have, okay, a cube root of x minus 1. Okay, we can also write this as x minus 1 to the 1 over 3, okay, because of being a cube root. So with that, okay, we can use a little bit of u sub. Okay, even if we use u sub, u equals x minus 1, this is going to end up as du equals dx, which means we can write this as integral from 1 to 2, okay, of u to the 1 over 3 du, which ends up, okay, oh, and actually, well, yes, I will keep those boundaries. I will just change the function at the very, very end. So now we have 1 over 3. Okay, we have to, again, use reverse power rule. So that 1 over 3, we have u to the 1 over 3 plus 3 over 3. Okay, I'm just adding it that way because that's essentially the same thing as adding 1. Okay, over 1 over 3 plus 3 over 3. That will essentially just be 4 over 3. Okay, now when I simplify all of this, well, of course, this is from 1 to 2. Simplifying even more, we have x minus 1 from, well, yeah, x minus 1 to the 4 over 3 over, and because this is a fraction here, we can actually send this 3 up, and write this thing as 3 over 4. Okay? And this goes from 1 to 2. So let's actually figure that out in the parentheses. Okay, little by little. We have, first, 3 times 2 minus 1. Okay, 2 minus 1 is just 1 to the 4 over 3 over 4. Minus 3 times 1 minus 1, which is just 0, 4 over 3 over 4. This guy is gone because we're multiplying by 0. Okay? So multiplied by 0. And this dude right here, okay? 1 to the 4 over 3, anything to the 1, well, 1 to the anything is just 1. So this essentially would just end up as 3 over 4. So the answer for this thing will be 3 over 4. Not bad, not bad, not bad. Wait, I maybe ruined this FRQ because I can't remember if I read that as square or cube root. It's alright. It's alright. It's completely fine. I don't think, in my opinion, I don't know if this question will get asked many points, right? Because it's actually pretty straightforward. So if you did, don't worry too much about it. Alright, next. Write but do not evaluate an expression involving one or more integrals, okay? One or more integrals that gives the volume of the solid generated when region R is rotated about the x-axis. Not bad. Pretty good. Straightforward. The good thing is it's rotated about the x-axis. Okay? It's being rotated about... Oh, sorry. Let me highlight that a little better. It's being rotated about this axis, which means that our radius will be the regular function f of x. Okay? That's where region R is. G of x isn't involved in region R, only f of x. Okay, and we go from x equals 1 to x equals 2. So this is actually going to be a piece of cake. Because we don't have an outer and an inner radius, we just have one single function, then we are again using disk method. Imagine using this method twice in an exam. That would be, it's impressive. So disk method, which means, okay, that because this thing is bounded and by the x-axis and x equals 1 and x equals 2, then those will be our a and b, right? That will be a, b. So you write pi of the integral from 1 to 2 of f of x squared. Okay, f of x squared dx. Now what is f of x squared in this case? Let's look back here. We have f of x equals the cube root. Okay, this is gonna be maybe a little bit of a tough one, but don't you worry, my friends. We'll walk through this together. So pi times integral from 1 to 2 of, so previously we saw how we had a cube root, right? So what to the 1 over 3. So technically we can write this as x minus 1 to the 2 over 3. Okay? Like at least I can get points within the correct setup for the question. Yes, that's true. If you perform a proper setup, okay, you can actually get some nice juicy points for that. So yes. Now, while I take a look at this, so basically this is what essentially what you will have to do. It's the exact same thing as we did previously. Pretty straightforward. Okay, so I'm actually just gonna kind of skip around a little bit about it. We have pi. Okay, pi. As you may have noticed, even though we used u here, x doesn't have a specific weird slope. So du dx is gonna end up the exact same way. We will still use u sub. Okay. But just to go a little more straightforward, I'm just gonna go straight to the exponent thing. So pi times, okay. So we have x minus 1 to the 2 over 3. Again, 2 over 3 plus 3 over 3. Okay. X minus 1 to the 2 over 3 plus 3 over 3. This ends up being 5 over 3, yes. And this over 5 over 3. And this goes from x equals 1 to x equals 2. Not bad. So that means that will be pi times, okay, so those are the 2 1 first. First you have 2 minus 1, okay, 2 minus 1 to the 5 over 3 over 5 over 3, and as I mentioned previously, you can treat this as the reciprocal, so you could just, let me actually move that a little more to this side. 2 minus 1 to the 5 over 3. Because you have a fraction here, you can send this 3 upward. So this is simply 3 over 5. Okay, not bad. And then the next one is essentially just a exact thing, 3 over 5. But this time is 1 minus 1 to the 5 over 3. Again, multiplying by 0. So this part is completely gone. So the unit I would care about is pi times 3. 2 minus 1 is just 1. Times 1 to the 5 over 3 is just 1. So 3 times 1 over 5. Which means that we have 3 pi over 5. That will be the volume of our... Okay, I may be a little bit of a fool because I just realized it says write but do not evaluate. Okay, so you guys may notice that from this point on I'm a little tired. But yes, even though we were able to figure it out, v is equal to 3 pi over 5, this will be good enough for the answer. Okay, again, my apologies, ladies and gentlemen. This will be good enough for the full points. Okay, setting the integral like that will give you good full points. So let me be very careful with the stuff that I'm doing right now, man. If the chat sees that I'm doing something wrong, please chat, tell me what I'm doing wrong, or just point it out. I will really thank you. Part C, right? We do not evaluate an expression involving one or more integrals that gives the perimeter of region R. Okay, that actually, I actually love that question. I actually love that question. Why do I love that question? Because it's related to something that I really like a lot. Unfortunately, I didn't mention it on the video, so my apologies there. But this talks about the perimeter of region R. This is something that I have actually never seen before. Because the region, okay, the region of R is all of these things. So let me actually highlight what the region of R looks like. You have this surface, right, going from 1 to 2, x equals 1 to x equals 2. You have this, okay, this vertical surface, which is going from 2 to 2, 1. And then you have this path. So what do you actually have to do here? Oh man, I think I just recovered a little bit of my voice. Great. So what do you actually have to do here? Well, first reason, between 1 and 2, you actually have just a unit of 1 here. This, okay, because this output, this 1, you also have another length here of 1. Okay, so that's already 2 parts of your perimeter. But then here you actually have to solve for the arc length. Okay? Here you have to solve for arc length. How do we do that? Well, first, the perimeter. Okay, the perimeter is going to be 1 plus 1, or just 2. Right, 1 plus 1 plus, and then you go for the arc length from 1 to 2 of f of x. And you may wonder, well, how do we do that? It's pretty straightforward, okay? But the actual integral for arc length, making that mistake helps us learn. Thank you. Yes, thank you very much, Alan, for telling me that. Yes, that's true. So you guys learn from my mistakes. Okay, going back to this thing. For arc length, when talking about arc length, the thing's actually pretty simple. If you go from certain x intervals, right, from a to b, the arc length looks like the square root of 1 plus f prime of x squared. dx. Okay, that's how you get an arc length. Okay? And well, you may wonder, okay then, pretty interesting. What's the actual derivative of f prime of x? Well, we're going to solve it just right now. So we know, okay, f of x equals the cube root of x minus 1. Yes, yes. Also known as x minus 1 to the 1 over 3. So let's just use our nice derivative rules. F prime of x, we're going to use power rule here. So this 1 over 3 goes forward. 1 over 3 x minus 1. Right? And then we have 1 over 3 minus 3 over 3. Right? We'll subtract 1. So 1 over 3 minus 3 over 3. This equals 1 over 3. Oh, man. Man, I'm hungry. I apologize if you guys hear my stomach. I'm just very hungry. So x minus 1. Okay? 1 over 3 minus 2 over 3. That's essentially just negative 2 over 3. Pretty good. With that said, you can already set up your integral by saying, okay, this is the integral from, okay, you remember this boundary here, this specific arc length goes from x equals 1, a, to x equals 2, b. So this goes from 1 to 2 of the square root of 1 plus, and in parentheses, you can put this in parentheses if you don't want to like solve for the whole thing. You have 1 over 3 x minus 1 to the negative 2 over 3. And this squared. Please don't forget that squared. If you did, it's fine. Okay? So this is the proper setup for finding your answer. The x And that's how you get your full answer for part C. Okay, you don't evaluate it, you just write it. Nice. Now we have evaluate the integral from 2 to infinity. Ooh! Fun fact, guys, I actually performed a little bit of research, like actual professional research on improper integrals, which are integrals that, have some boundaries related to infinity or stuff of sorts. Okay? But that's not the point. Let's take a look at the actual stuff in here, the cool stuff. So, we know that g of x, okay, let me actually write it down here so we don't have to go up over and over. G of x equals e to the negative 2x plus 4. Let me just make sure about that one. Yes, sir. Now we have to find the integral from 2 to infinity. Okay, from 2 to infinity of e to the negative 2x plus 4 dx. Okay? And this will be as straightforward, okay, as just thinking of this infinity as a limit. So limit as n goes to infinity of the integral from 2 to n of e to the negative 2x plus 4 dx. So little by little. First, u sub. You see this thing is inside of e to the x? That's u sub. So say u is equal to negative 2x plus 4. Okay, du equals derivative of this, so negative 2 dx. Okay, which means dx is the same thing as du over negative 2. So we can actually take that out of the equation, solve it later. Okay, we can say limit as n approaches infinity of a negative 2 of the integral from 2 to n. Okay, and don't worry, I'll bring those, what do you call this thing? I forgot the name of this. Actually, wait. No, for this one, I actually will change the bound limits. So how do we actually change the bound limits? You just plug this x value into your u. So for example, here, u equals, well, u at x equals 2 equals negative 2 times 2 plus 4. This is just negative 4 plus 4, which is 0. So pretty good, actually. This is 0. And then for the other guy, u at x equals n is just negative 2n plus 4. Okay? Pretty simple. Negative 2n plus 4 of e to the u du. Okay, what do we do afterwards? We just solve our integral. E to the u, integral of e to the u is just e to the u. Exact same thing. Wonderful thing about e to the x. Okay, so we have negative 2 times e to the u from 0 to negative 2n plus 4. Not bad, not bad. Pretty good. We'll have to be negative 1 over 2. Wait, negative 1 over 2. Am I missing a specific part? Negative 1 over 2. Oh, wait, you're saying like the answer, the overall answer has negative 1 over 2? I'll figure out in just a second. I'm not there just yet. Okay? So, let's actually do this. Oof, man. We have negative 2, big parentheses. Okay, again, the limit thing. Infinity, negative 2. No, in front of the integral. Negative 1 over 2. Oh, you're right. Thank you. Thank you very much. Thank you so much for letting me know about that. Yes, it is indeed negative 1 over 2. My apologies. Sorry about that one. Yes, negative 1 over 2, negative 1 over 2, negative 1 over 2. Thank you. So with that in mind, thank you very much for the chat for helping me out there. Then we work with the actual integral. So we just plug that stuff in. E to the negative 2n plus 4. Okay? That's one of them. Minus e to the 0. Not bad. Because I had information what the integral of a rate of change and net change. Yes, essentially. That sounds pretty good. So, okay, we're getting closer and closer to our final answer. First, e to the 0 can also be just 1. Okay? So, limit as n approaches infinity of negative 1 over 2. This part you can simplify it, because this 2n, since n is infinity, we're talking about e to the negative infinity here. Okay? Also known as 1 over e to the infinity minus 1. And because we have e to the infinity, that's just going to be 1 over infinity. And we know that 1 over infinity, usually in this sort of context, equals 0. So, final answer, this is just 0, becomes 0. Well, yeah, this whole thing 0. Let me actually highlight it this way. There you go. Or maybe that was an MCQ. Maybe. There we go, 0. Limit as n approaches infinity of -1/2 of -1, which at the end equals, so that's just making things positive, so 1/2. So at the very, very end, okay, the answer for part D there is 1/2. So the integral here, the integral from 2 to infinity of g of x dx equals 1/2. Pretty nice, pretty wonderful. All right, let's take a look. So this was essentially, ladies and gentlemen, all of the BC FRQ, the BC FRQ number 5. Let me again take the screenshot and export this. Not that, this. PDF 5 BC. There we go. We export that. We export those. Nice. So how are we feeling, chat? We're feeling comfortable. We're feeling cozy. What if I didn't change my bounds on my integral because I plugged you back in? In that case, as long as you didn't change your bounds and you plug your u back in, you're completely fine. Okay? I just did it that way so we can like get to the math a little easier, right? A little more simpler. But if you just plug u back in and then solve for your bounds, also gets 100% on the BC exam. Okay? Don't worry about that. So, ladies and gentlemen, we're already getting closer and closer to the end. I am hungry. I hope there is some lunch after this, or lunch and dinner. I kind of forgot the combination between lunch and dinner. So now we're going to take a look at the AB FRQ. Oops, sorry. AB FRQ number 6. Nice, nice. Pretty good, pretty good, pretty good. Okay, let's take a look at that. We have our nice AB right around here. Let's take this guy out just for a minute. Okay, this is our last question for the AB exam. Are you guys excited? I am excited. Let's go! It's an easy question. Okay, now definitely I am excited. Now definitely I am excited for this. This is an easy question. The function f is twice differentiable, and they give you a nice table with f of x and f prime of x. First, find the limit of x as what? Of x as x goes to 2 of f of x over x, or state the limit does not exist. Well, we'll see. In this case, that would just be the limit as x approaches 2 of f of 2 over 2, which equals, well, f of 2 you can see in the table, f of 2 equals 3. So we have 3 over 2. And yes, that's essentially it for part A. Boom! Absolute cinema, also absolute calculus, ladies and gentlemen. Then we have g of x. G of x is equal to f of x. Oh, I like that. I like composite stuff. So g prime of 2. Well, first let's figure out what actually is g prime of x. And because we have composite functions or functions over functions, we're using chain rule here. Okay? So we'll have f prime of x. Okay, f prime of f of x. That times the baby, right? The baby. So it'll be f prime of x. You're 17? That is true, my friend. I am 17 years old. So, going back to this thing, we have f prime of f of x times f prime of x. It's kind of weird to actually say, but little by little, we're figuring the thing out. So, g prime of 2 equals f prime of f of 2 times f prime of 2. So let's actually figure those out. First, f prime of 2 equals 4. So that guy right there will be 4. But first, let me actually start like from left to right. Sorry about that. So f of 2, we know that's 3. Okay? Therefore, here we're figuring out f prime of f of 2, which is 3. So f prime of 3 times f prime of 2. That's pretty good. That's pretty nice. So with that in mind, let's actually solve for those. F prime of 3 equals 9 times f prime of 2, which equals 4. 9 times 4, my good friends, equals 36. This will be the answer for part B. Pretty straightforward, pretty nice and easy. For part C, we have let h be a differentiable function such as h of 0 equals 10 and h prime of x equals f prime of 3x. Find h of 2. All right, let's take a look at this. So for h of 2, okay, this is kind of a tough one, man. But it's all right. So first, let's think in context. What's h of x? Okay, well, we know what h prime of x is. That is indeed f prime of 3x. But what if we try to take the integral? Okay, why don't we try to actually take the integral of this dude right here? Okay, of this dude man. Okay, let's actually try to do that. So let me actually bring this here. Move to this side so I have a little more space for working. If I do so and take the integral of these two sides, I have to do so very carefully. Of course, both of them in terms of x. So on the one side we have h of x, but on the other one, okay, we still have f prime. Okay, and with the flip is f prime, man, I don't know. Well, it's all right because we can use u sub. Okay, u equals 3x, du equals 3dx, dx equals du over 3, which means that this guy right here will look like integral of f prime of u du, right? Don't forget about that 1 over 3. Okay, and when dealing with that, then you get the answer that h of x equals 1 over 3 times f of u. Okay, but you can plug u back in, and remember u here is 3x. Nice, pretty good. And now, oh wait, actually, not yet. We're missing something, ladies and gentlemen. We're missing the plus c. We can never forget that. So we're missing the plus c. That's why they gave us this h of 0 equals 10, because that's going to make this 10 times easier to figure out. Okay, h of 0 equals 1 over 3 f of 3 times 0. That's just going to be 0. Okay, 3 times 0 is going to be f of 0 plus c. So let's look back. What's f of 0? F of 0 here is -1, which means that h of 0, my good friend here, that's 10, right? 10 equals -1 over 3 plus c. All right. I swear I had a very similar question MCQ. Likely, there is a high chance. So looking back to this, we have this 10, we have this -1 over 3, we have this c. So let's start thinking. Okay. So this 10, we can also rewrite it as 30 over 3. Okay, just to make things a little nicer when you do the subtraction. Because afterwards, okay, after doing that, then you get, 30 over 3 plus 1 over 3, right? You just like send this thing to this side, but opposite sign, or just add 1 over 3 on both sides. This equals c, which means that c here equals 31 over 3, if I am not wrong. Right, you're adding, 30 over 3, that's 10, plus 1 over 3, that's 31 over 3. Excellent. Let's go back. So now we know that h of x equals 1 over 3 f of 3x plus 31 over 3. I like this. So now let's actually solve for h of 2. h of 2 equals 1 over 3 f of 3 times 2 plus 31 over 3. So let's take a look. 3 times 2 equals 6. What's f of 6? Okay, let me actually simplify that. F of 6 plus 31 over 3. Let's take a look. What's f of 6? F of 6 here is equal to 5, which means that my final answer here will be 1 over 3 times 5 plus 31 over 3. If I simplify that, we have 5 over 3 plus 31 over 3, which leads to 36 over 3, which leaves in a wonderful number, which is 12. I love when questions end in numbers like these. So now we know that h of 2 equals 12, ladies and gentlemen. Not bad. So let k be the function defined by k of x equals the integral from 0 to x of t squared f of t dt. This is a tough one, but I like it. So, find k of x. According to the fundamental theorem of calculus, the derivative of an integral is just the stuff inside of the integral. So, k prime of x equals d dx of the integral from 0 to x of t squared f of t dt. And I mentioned this in my video. If you have something in this top boundary that's not x but something different like x squared, you will use chain rule and plug that actually into your integrand after you cancel the integrals out. Okay? But here you only have x, so it's as simple as plugging stuff in. So in this case you have t squared, right? So that it becomes x squared times, not plus, times f of t, or in this case, f of x. There we go. So that is k prime of x. Now, k double prime of 3 is a slightly different question. It's crazy that it wasn't a chain rule question. There's like, huh, interesting. Anyways, so k double prime of x, okay? Now we're multiplying functions here. So this is product rule. We have to use product rule. So I usually go, these little arrows, right, for taking the derivative. So x squared times f prime of x plus f of x times derivative of x squared, which is 2x. Not bad. I don't have to simplify it if I just keep going and do k double prime of 3, which equals 3 squared f times, 3 squared times f prime of 3 plus 2 times 3, okay? Let me do that part first. 2 times 3, that's 6 f of 3. So let's take a look back. Okay, this 3 squared can be written as a 9. So now this is equal to 9 times f prime of 3. What's that? F prime of 3 equals 9 as well. Look at that. So that's 9 plus, 9 times 9 plus 6 times f of 3. What's f of 3? F of 3 here is 8. So that's this thing right here. There we go. 6 times 8. Which means that 9 times 9 is 81. 6 times 8 is, if I'm not wrong, 54. Okay, I'm actually going to do a little bit of, you guys shouldn't do this on the exam, but I will make sure that I got that right. 6 times, oh wait, no, it's not 54. It's 48. It's 48. It's 48. I just remember my tables. It is 48. There we go. It's 48. 6 times 8, 48. I knew it. Nice. And when you simplify that, 80 and 40 is 120. 1 and 8 is 9, so 129. This, my friend, okay, is the answer for all of part D. And that is essentially how you solve the very last question in the AB FRQs. Brother, I need some water. This is very interesting, though. I do like the fact that we ended in a single number. Let me just make sure that I did get that right. 81 plus 48. 48. That is indeed 129. Excellent. So, again, we take those. We zoom in a little and take the pretty screenshot. Wait, save that there. And we export it to PDF. There we go. So this is number 6. Not 7. I wish it would imagine there was a 7 FRQ. I won't like that. AB. Not bad. Pretty good. So, whew, my friends, we are one FRQ away to finishing the stream. Are you guys ready? Hopefully you guys are ready for this very epic moment. Let's go to the very last one. As you may have guessed, the very last one is related to series. Wonderful series. I love them. So let's take a look at this. The Maclaurin series for a function g is this pretty thing, right? And converges to g of x for absolute value. This one killed me because I used the wrong error bound. No! Oh no! The error bounds. I also dislike the error bounds a lot. It's alright though. It's alright. We're going to take a look at this now. So, the Maclaurin series for a function g is given by this long thing that I'm not going to talk completely because my voice is already destroyed, and converges to g of x for absolute value of x that's less than 5. First question is, for x is greater than 0, the Maclaurin series for g is an alternating geometric series. I think we can tell. And we have to find g of 3. So we actually just plug that x equals 3 right in here. So we do that, right, the summation from n equals 0 to infinity of 2 times negative 3 over 5 to the n. Okay? Now the good thing is that with this, okay, finding g of 3 is actually pretty straightforward because we have to just essentially do a nice and easy, how do you call this thing? I forgot the name of this. Oh, no, not remember it. Geometric series, right? Well, of course, we're working with geometric series right now. I just have to actually remember the name of the thing. But yeah, for geometric series, you always use a over 1 minus r. A is your initial value. In this case, our a here is 2. Okay, that's our a here. And then our common ratio r, which in this case is going to be this guy right here. Okay, r. So let's start plugging in stuff. We have a2 over 1 minus r. In this case, r here is negative 3 over 5. So you have to actually write plus 3 over 5. Right? We're subtracting a negative. That's what we're adding. So, with that in mind, okay, we can actually kind of simplify this thing. We can take this 1 and make it a 5 over 5. Okay, this is just 1. Essentially just 5 over 5. Let me actually do that with a different color. It's 1. So when we add those, we get something that looks like, not what I'm looking for. Sorry, the pen. 2 over 5 plus 3, that's 8 over 5. Because you have that fraction in there, you can send this thing to the top. So now you have 2 times 5 over 8. That looks like 2.5. Let me actually correct that. 2 times 5 over 8, which equals 10 over 8, which equals 5 over 4. If I'm right. Yes, I'm right. Yes, I am right. Excellent. Pretty good. So this, my friends, is going to do part A. Whew, for part B, they say the function f is defined by f of x equals g prime of x. Write the first 4 non-zero terms of the Maclaurin series for f. Let's do so. So, they essentially just ask us to get that g, right? Get that little g part and take its derivative. Okay? And you may think, oh, wait a minute. This thing looks very, very complicated, man. But don't worry. It's actually very, very straightforward. Okay? Because when you're trying to figure out the derivative of a series, right? Series like this, for example, a power series or Maclaurin series, then you have to think about it in terms of like the context of what we're actually doing. Okay? Here we're doing g prime of x, which is essentially the summation. Summation. This is just b, by the way. Let me just highlight that. N equals 0 to infinity. Okay? Of 2. And here you may notice you have negative x over 5. Okay? You have negative x over 5 there. But you also have an exponent n. The way you will usually do this is you send n forward. So now you're multiplying 2 times n. Okay? 2 times n. You keep that negative x over 5. And now you have n minus 1. Okay? This is pure power rule. Now, we don't stop there just yet because we also have to multiply by the derivative of the inside. And our inside was negative x over 5, which means we multiply by negative 1 over 5. That's the derivative of this guy right here, of this negative x over 5. So, how do we actually write this? Well, we can just first simplify it a little, right? We can write this thing as negative 2 over 5. Okay? Negative 2 over 5. N, okay, negative 2 over 5 times n, or negative 2n over 5, also completely valid, okay, times negative x over 5 to the n minus 1. This, my friend, is f of x. This is a summation of all this thing, n equals 0 to infinity. But now we have to write the first 4 non-zero terms. So let's go for those, okay? Let's go for those. So for that, we're going to go term by term. And funny enough, unfortunately, I just realized. Okay, quick highlight. What I just did there is I just took the derivative of the full actual, like, general Maclaurin series. This is not 100% required because that's not what they asked for. They only asked for the first 4 non-zero terms. So what will work 100% is if you just take the derivative of these guys that already give it to you. Okay, sorry about that. Those are just 2 ways of doing it. My way was just very, very much longer, so my apologies for that one. I'm just very tired, so let's keep going for that one. Okay, and actually, let's actually do both ways. Okay, for this one, we just plug in 0. I did that too. Thank you, Dan. Now I feel like I'm not alone. Thank you. But yeah, you guys learn from my mistakes, so essentially, that's how the thing goes. If n is equal to 0, then this thing is everything is just gonna cancel out. So we're gonna jump to 0 plus, okay, and then the next term. So what's our term here? N equals 1, we have negative 2 over 5. Okay, negative 2 over 5 times negative x over 5 to the 1 minus 1. So that would just be 0, which makes this thing 1, and we're just subtracting negative 2 over 5, which you may notice aligns with what if we take the derivative of this guy right here. That will also be negative 2 over 5. Okay? And actually, I regret it. I'm not going to finish this general term form. I'm just going to take the derivative of these guys. So 2, derivative of that 0. Derivative of negative 2 over 5x is negative 2 over 5. Derivative of this guy, well, we send this 2 forward, so 2 times 2. So that becomes 4 over 25 times x. This thing, okay, derivative of this thing, very similar. 3 goes forward, so 2 times 3, that becomes 6 over 125. Okay, x squared. Let me actually take this 0 out. There we go. And then this thing, right? X to the 4th, send that 4 forward, so 2 times 4 equals 8 over 625 times x cubed. Okay? And if you bother to do all the calculations, you may notice that yes, this is the thing that you end up with at the end. This will give you full marks for part B. Again, my apologies if I did the general form. Sometimes in previous AP exams, they will ask for general form, but in this instance, you might as well just take the derivative of all of these symbols, which gives you the exact same thing. Okay? That's for part B. For part C, we get to the error bound. Oh man, this is not great. So here's the thing that I am a little ashamed of myself for, but it's alright because that's how humans are. I don't remember error bound quite well. Okay? I do know this is Lagrange error bound. Actually, no, it isn't. I'm lying. I am very much lying. Or am I lying? I'm not quite sure. Oh yeah, no. It is. Because this is not essentially just a series for any type of series, right? This is technically a Taylor polynomial for f. Specifically for f. So let me highlight that part. Okay? The second degree Taylor polynomial for f is used to approximate, okay, f of 5 over 2 as negative 3 over 10, where f is the function defined in part B. We already did part B previously, okay? So then to say justify that f of 5 over 2 minus negative 3 over 10 is less or equal to 1 over 5. So if I'm not wrong, okay, if my math doesn't fail me, here we use something called Lagrange error bound. Okay, Lagrange error bound. Essentially, just a way to show you approximately by how much. Okay, by how much did we think that was our approximation off by? Okay, and you may notice, well, how do we actually do this? Okay, it's actually pretty straightforward. Let me actually kind of pop up a picture here that will show you how the thing actually looks. Okay, so yes, there we go. So this is out of the Lagrange error bound. This I give credits to Exomath, okay, for this nice thumbnail. Okay, it's right here. This is the error bound, okay. Credits Exomath. Thank you. Okay, this is how the Lagrange error bound works. Okay. And it is a little complex, and actually I just realized that this version doesn't have what I want, so I'm actually going to copy a different version. Still Exomath, thank you very much for your for your assistance. So, oh, this is much better. This one already has a watermark, so thank you, Calc Workshop. I actually like their website a lot. I used to study it pretty much when I was taking this thing. When I did this, I found a big positive number because I use alternating series because it's one of... Oh, yes, I get your confusion. So this one, we don't use alternating series here, because this is a Maclaurin series, or also a Taylor polynomial. Therefore, we actually use Lagrange error bound. Okay? So, what are we going to do here? Okay? What are we actually going to do here? Well, let me take a look at this carefully, because I want to make sure I am understanding this question right. I may get something wrong, and I don't want to do that. Okay? So for these, it's less or equal to 1 over 5. Okay, I see. Interesting. So this is about x equals 0. Okay, that's 5 over 2. Okay. I think I see where this is going. I believe I see where this is going. So, yes, I see where this is going. So, here's a cool thing, ladies and gentlemen. First, they give you a degree. They told you this is a second degree Taylor polynomial for f specifically. Okay, so here on degree, n is going to be equal to 2. Okay? Usually this part here, this specific section here, represents the remainder. Okay, that error. we have to make sure that this error is below, okay, we have to justify that this error is below the, or equal to 1 over 5. Okay, how do we do that? We use this chunky formula right here. Okay, so first we have our f of n plus 1. We know that n is equal to 2, so this is just 3 of z. I'm going to explain what z is in a second. Okay, times the absolute value, okay, between, sorry, give me a minute. Ooh. So this is a centered about x equals 0, pretty good. And x, so x here is our given value. And in this case, x will be 5 over 2. Okay, that's essentially where we're trying to approximate this thing. So this will look like 5 over 2 minus a. A is where the polynomial is centered. But our polynomial here is centered at x equals 0, so we don't bother about that one. And that to the n plus 1, right? 5 over 2 to the n plus 1. Again, n was equal to 2, so n plus 1 would be 3 here. To the 3 over, okay, let me actually write that z a little more specifically. Z, better. Over n plus 1 factorial. Again, 2 plus 1 is 3, so this will just be 3 factorial. Okay? And then you may wonder, well, what the flip is f cubed of z? What does that represent? Okay, what that represents here specifically, okay, what it represents specifically is the maximum value between a and x of the third derivative of f of x. Okay? Z is just some number between a and x, but f cubed of z here, okay, and not cubed, technically it's not cubed, it's actually just the third derivative. Okay, the third derivative of f of z here, we're looking for the maximum, okay, of the third derivative of f. That's essentially what we're doing here. How to do this properly? That's where I was kind of like a little slightly teeny tiny bit confused, okay? But from my understanding, okay, from grabbing that third polynomial, okay, we can actually kind of go back to this thing. We can go back to this nice looking thing, right? These approximations. And you have to take a look, okay, at what f actual f prime, well, f, the third derivative of f is, okay? So here, this negative 2 over 5, that's the first derivative of f, okay, f prime. This thing is f prime. If I'm not wrong, that's f prime. Yes, I believe so, yes. This one is f double prime, and this one is f triple prime. Okay? This one is f triple prime. Oh man, I'm a little comfortable. There we go. So that one is f triple prime. Okay, just take a look at them little by little, because if I remember properly, okay, f itself was just how do you call this thing? F just turned out to be 0. That's how the thing started here. That's how we ended up with this thing. Okay? Now, I believe that the approach I want to go for here, because technically this one is a non-calculator question. I'm just want to take a look at something. Oh, okay. I see something here. I see a piece of information that I didn't take a look at before. Okay? Something to highlight, okay? Something to highlight a lot is that they try to use, okay, so the value here, they try to approximate f prime of, f of 5 over 2, okay, is used to approximate at as negative 3 over 10, okay, as negative 3 over 10. So the thing looks a little weird, but I believe what you would have to do here is use this negative 3 over 10 as our maximum value of the third derivative of f of x, okay, between a and x. Now, here's the thing. I actually don't think I'm doing that right. Actually, no, I think I am doing it right, because that itself, the maximum here, is negative 3 over 10, okay? I'm just a little rusty on Lagrange error bound, so my apologies if people in the live stream are not so surprised about my poor calculation skills in here. But yes, so I believe that's essentially what you will have to do, okay, if I am not wrong. So if we do this, okay, if we actually use that as a maximum, okay, as the maximum value and so on and so forth, we write -3/10 times, and we can actually kind of just cube all of these. For example, 5 cubed, that will be 125, over 2 cubed, that will be 8. And this divided by 3 factorial. 3 factorial is just 3 times 2 times 1, which is just 6. Okay? Let's actually simplify this a little. So we have -3 times 125, that will be a total of 375, if I am not wrong, over 10 times 8, which is 80, times 6, which is 480. Okay? Now, here's the thing. I am not quite sure of what this decimal actually is. So I may have to simplify it a little bit, well, more considerably. I might have to actually simplify it a lot. Unless I can state that this thing, okay, unless I can state, because I know that this is a lot regarding absolute values. Oh man, my throat hurts. Okay, I gotta be kind of honest with you, chat. I am not quite sure about how to do this question. I'm not quite sure about how to do this question. So here's what we're gonna do. I'm gonna try and perform a little bit of research because I'm actually pretty confused about this one. Okay, let's take a look at this. Oh man, my neck hurts a lot. Well, more like my throat. Okay. Yes, perfectly. Okay, now I got it. So here we have to show that the error is less than 1/5, as I mentioned previously. So I actually did get, okay, I actually did get this part right, the 3 factorial, all of this, that is proper, that is correct. But we have to explain how this thing right here, okay, is less or equal to 1/5. Okay, and here's the thing. Even though we don't exactly have the maximum of the third derivative. Whew, sorry, give me a minute. Ugh, man. Yeah, I need more water. I already drank 2 bottles. Okay? Basically, what I have to state here, the maximum of the third derivative of f was likely determined to be small enough that when multiplied by, multiplied by 125 over 8. Okay, it's 125 over 8, which is this 5/2 cube that I already previously did, and divided by 6. This result is less or equal to 1/5. So chat, I do want to apologize because I don't know if I knew this thing completely, okay, about the Lagrange error bound, but essentially you just have to set this thing like this, right? Demonstrate how to actually, how the maximum of this thing behaves, right, in terms of the error here, okay? Divide by 4 factorial. Technically, from my understanding, we have to divide by 3 factorial. Okay, because here we're working with the second degree Taylor polynomial. Okay, so that means an n is equal to 2, and we go for the one after that. In this case, it will be 3 factorial. Okay? Ooh, man. Oh, give me 1 second. So, here's the thing. Damos, I apologize, but not even I know 100% of what I did here. For example, this question is a question that I will have likely skipped because I didn't know Lagrange error bound quite well. But this is essentially the logic, okay? You have to demonstrate how this, okay, how the remainder, how this little approximation here, it's 3, I choked on the test. It's completely fine, Jordan. I think you still got this, okay? But this is essentially what you have to state, okay? As long as you remember this formula, okay? And maybe try to explain a little how this is just less or equal to 1 over 5, okay? Then you should be good, okay? That's essentially how this thing works. You have to, they give you an error bound. That's what the thing is called, error bound, okay? Error bound. So that means that this little thing, okay, this little decimal you will have to get has to be a little less than this, less than the error, right? So that, writing this specifically, okay, this, I believe, to get you close, okay, not full, because not even I know, it's close to full marks, okay? Likely, if I do find out the proper answer for this question, I will show it to you guys maybe in a different moment. Flip the calculator portion, but non-calc, I guess, on 5 because of time. Fair enough. 100%, that's something I will have done. Time management is something very, very important in this thing. Okay? Anyways, let's take this thing, send it here. Let's deal with the very final part of our wonderful, wonderful 4-hour stream. Oh, brother. Longest lecture I've ever had with my good fellas. So, the function h is defined by 25g of x minus 2e to the x. First, I read the first 3 non-zero terms for the Maclaurin series for e to the x. So, this one's actually pretty simple. Calc part was too easy this year. I had 25 extra minutes at least. Wow. Fair enough, fair enough. That's what happened to me for multiple choice. For the free response questions, I did have to take my time. So let's take a look. For this one was the GOAT. Didn't touch my TI-84. That's true. Desmos is always the GOAT in any exam related to math that's standardized. Okay. Anyways, first 3 non-zero terms of the Maclaurin series. As you may remember, okay, the Maclaurin series of e to the x looks like this. Something you should have memorized, which looks like x to the n over n factorial, which means that the first 3 non-zero terms, okay, will be x to the 0 over 0 factorial, which is essentially just 1, plus x to the 1 over 1 factorial, which is just x, plus x squared over 2 factorial, which is just the exact same, right? X squared over 2 factorial, or just x squared over 2. There we go. I can do polar and decimals. So technically, you can. Technically, polar and decimals is possible. You just gotta be a little more careful. Previously in the stream, we did deal with how do you call this thing? With polar, and we used a little bit of decimals with it. Okay. But we did take a look at it previously. It's just a little hard to actually kind of manage. But yes, I get your point. So I believe this I, okay, will be the first 3 non-zero terms for the Maclaurin series for e to the x. They kind of look like this. Okay. Essentially, oh, sorry, I need the. Man, my voice. No, my voice is going away. So that will be the first 3 non-zero terms for the Maclaurin series. But then they ask you to write the first 3 non-zero terms for the Maclaurin series for h. Okay? And you may wonder, well, how the flip do we do that? Okay? And it's actually pretty straightforward because you have to go little by little, term by term. Okay? When going for I2, like I, okay, you have to do h of x equals, and you go term by term. So I'm actually going to use parentheses for each term, okay? For each term. So this is the first term. So for that one, you have to understand, okay? Oh, man. That hurts. That hurts a lot. Help. Okay, let me take a look at something because I may be a little wrong. For I use decimals to find the bound of the area. I just did the integral. My answer was like 1.6 or 1.7. Oh, actually, that is, I believe, something that we saw in the stream. And I believe you were correct. Okay, you can always rewatch it. If not, after the stream, I'm going to use a couple of timestamps so that people that didn't watch the stream can always take a look at those specific answers, okay? So, yeah, good job right there. Well, let me take a look at h of x specifically because I may be doing something wrong and I don't know what it is. Okay, but hopefully I am not. Actually, I'm. Oh, actually no, I'm not. I'm not. I'm just doing the thing a little more different because here's the thing: if you want to find the first 3 non-zero terms of the Maclaurin series, then you have to just plug in the first non-zero terms, right? The first 3 non-zero terms for g of x. Okay. My room code has literally 7 in it. Oh brother. Oh no. Oh lord. Anyways, as I was mentioning, you grab these 3 fellas and write 25. 1 plus x squared over 2 factorial. Actually, no, I almost did that wrong. This is g of x. Okay? This is g of x. You have to approximate both e to the x and g of x. So e to the x will already have it, but g of x, okay, that's actually all the way here on top. G of x, those first 3 non-zero terms are these 3 dudes right here. So let's write those. We have 25 times 2 minus 2 over 5x, I believe, yes. So plus 2 over 25x squared. Plus 2 over 25x squared. Okay, those are the first 3 non-zero terms. And then, okay, and then you write plus 2 times e to the x. Okay, 2 times e to the x. But the three non-zero terms for e to the x are these guys. Okay, so you do 2 times 1 plus x squared over 2. Okay, so let me actually simplify these things. First, we have 25 times 2, which is 50, minus 25 over 5, which is 5, times 2, which is 10, times x. Okay, let me actually kind of do something kind of cool. I might do this, that, and then for the blue one, this and this becomes this. Okay, 25 times that. Let me take a look at this. There we go. It says Monday. All right, pretty good. So 25 over 5, that would be just 5 times 2, negative 10x. And then very last one, okay, let me actually do that one with purple. Okay, that one goes here. Oh man, my fingers already kind of get a little weird. Okay, 25 over 25 becomes only 1, so we have plus 2x squared, right? And then you add all these other dudes, right? For the other dudes, you have plus 2 times 1, that's 2, plus 2 times x, which is 2x, plus 2 over 2, which is 1, times x squared. So plus x squared. And at the end, you just combine like terms. Combine all these guys by terms. So you have 50 plus 2, 52. Negative 10x plus 2x, which is something like negative 8x, if I'm not wrong. Yes, negative 10x plus 2x. Yes. And last but not least, 2x squared plus x squared becomes 3x squared. Ladies and gentlemen, we have officially finished every single FRQ that show up on the exams given by CollegeBoard. Okay, my apologies if I wasn't able to cover yours. I'm going to take a last screenshot for this. Man, I'm tired and I'm hungry. There we go. Screenshot, and we export this thing. So, FC BC. There we go. Sure, did I have enough time to simplify this question? Will I still get points? Yes. Yes. Something that the exam mentioned previously is that even though you don't, there's no need to simplify. Either numeric or algebraic, you don't need to simplify. Okay, as long as you give your answer straight to the point, 100%, like you get the full points. Okay, you don't need to simplify. You can, but you don't need to. It's not 100% required. Okay, but yes. So guys, it was an honor. Okay, let me actually change back to the stream, main cam. There we go. Ladies and gentlemen, it was an honor to be with you. Thank you very much for coming to this wonderful, wonderful stream. Deimos, if you're wondering what math I'm in, I am in, well, technically I graduated by finishing AP Calculus BC. So yes. But guys, thank you very much for staying for the live. And for those people who are watching the replay, thank you very much for taking a look at all these things. Sorry if I committed a few mistakes on the way. I thought it was going to be a little easier, but at the end it was 4 hours, which was not 100% simple. But still, thank you very much for staying there. You always learn from my mistakes, or you learn from your own mistakes. Thank you very much for coming to the live, and please have a wonderful, wonderful day. Take care, fellas. I know you did great on the exam, okay? And just check the channel because there are a couple more surprises that I want to show you guys, okay? Take care.